A tiny dip in starlight from Leo just lit up the biggest alarm in astronomy. K2-18b may be shouting life from 120 light-years away. James Webb saw something in that atmosphere that, on paper, carries a 99.7% chance of biology. But is this humanity's first living world or a cruel cosmic mirage? And what would it take to turn that signal into undeniable proof? Some discoveries arrive like thunder. This one arrives as a barely visible pattern, and it refuses to go away. In the infrared, a distant world leaves a signature so delicate that belief and doubt begin sharing the same breath. Tonight, we follow a trail made of subtraction, light measured, light missing, and meaning argued over in the margins of noise. K2-18b is not a photograph, not a landscape, not even a point of light, only a rhythm. Yet within that rhythm, Webb reads a spectrum where physics becomes inference, and inference becomes temptation. Each transit turns a thin ring of atmosphere into a laboratory tube, and the results arrive as a barcode. But barcodes can be smudged by clouds that hide the deeper layers, by temperature gradients that bend the lines, by a star that refuses to sit still. The number that captured the public imagination is not a verdict delivered by nature, but a statement conditioned on models. It lives inside assumptions about chemistry, about haze, about what the telescope is truly seeing, and what it is merely averaging. To take it seriously is to do something harder than wonder. We must define what would count as proof, because life is not a single molecule, and it is not a single feature at a single wavelength. It is a claim about persistence, about disequilibrium, about an atmosphere being held away from easy chemical rest. That is a high bar for a world we can touch only with photons, and a bar that history warns us not to lower. Across this film, we will move step by step along the inference chain, from geometry to chemistry to competing explanations. We will watch how a planet's size is extracted from a dimming that lasts hours, and how its air is inferred from differences measured in parts per million. We will confront the ways an active red star can paint false colours onto a planet's spectrum, and the ways our own expectations can do the same. Then we will ask the question that makes this story more than a headline. What would it take, scientifically and philosophically, to transform a probabilistic signal into humanity's first confirmed evidence of life beyond Earth? The closer we get to an answer, the more the universe demands discipline, replication, skepticism, and tests designed to fail the claim before we let it stand. This is an exploratory journey into a new kind of discovery, where the frontier is not distance alone, but certainty itself. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We'll begin with the simple shadow that reveals an unseen world, then follow Webb's methods into the chemistry of alien air. And before any conclusion is allowed, we'll trace the hard tests ahead, because extraordinary implications require extraordinarily resilient evidence. A star brightens, then dims by a fraction too small to feel, yet too precise to ignore. On a graph, the change looks almost insulting, an eyelash-width notch cut into a smooth line. The dip lasts hours, repeats on schedule, and returns like a metronome in deep space. Nothing explodes, nothing flares, and nothing looks dramatic in a telescope image. Yet the pattern is a signature, and signatures can be translated if the instrument is steady and the interpreter is careful. This is how many exoplanets first announce themselves, not as worlds, but as math. A planet crosses its star and steals a thin slice of light, and the star's brightness drops by a measurable percentage. That theft is called a transit, and it is recorded as a light curve, a timeline of brightness versus time. The smaller the drop, the harder the claim, because the signal must be separated from instrumental drift and the star's own restless surface. Even a quiet star has spots, granulation, and subtle pulsations, nature's noise layered on top of the planet's shadow. A transit is also geometry made visible. The depth of the dip is mostly the ratio of areas, the planet's disk compared with the star's disk, which is why a larger planet carves a deeper notch. The duration of the dip hints at orbital speed, which depends on the star's mass and the planet's distance. The exact shape of the dip, including how quickly it begins and ends, can reveal whether the crossing is central or grazing. In that curve, astronomers read size, orbit, and alignment, an entire system inferred from a temporary dimming. In the constellation Leo, a familiar marker on star maps, a particular star shows that repeatable dimming. Leo is not a destination, only a direction, a way to point a telescope and agree on a patch of sky. On screen, it is a pattern of bright points connected by imagined lines, a lion drawn from ancient navigation. Behind those points, the real scene is three-dimensional and scattered, with stars at different distances that only appear neighbours from Earth. The system sits about 120 light-years away, far beyond any probe, yet close enough to study with modern instruments. The photons reaching us tonight left when the world was 120 years younger. That time lag is not poetic. It is the basic constraint of astronomy, and it governs every claim we make. We never see the present, only the last delivered message, and the message arrives already aged by distance. Every measurement is a delayed report, and every conclusion is built on old light, processed through detectors and algorithms. The question is whether old light can still carry new truth, and whether our methods can extract it without adding our own illusions. The planet tied to this dimming is known as K2-18b. At first, K2-18b is not a landscape or an ocean or a cloud deck, because nothing in the data contains an image. It is an inferred radius, an orbital period, and a probability that the signal is real. It is a shadow that should not matter until it does, because shadows are the first step toward atmospheres. When the transit repeats, it becomes a clock, and the clock invites deeper questions about what is circling the star. The claim attached to K2-18b is the kind that spreads faster than the data. A 99.7% chance of life sounds like a verdict delivered by statistics, crisp and final. It sounds like we are one decimal place away from certainty, as if the universe has already signed the paperwork. It also sounds like a trap because numbers can be precise and still be misread, especially when they are detached from what was actually tested. In science, confidence is not a feeling, but it is also not a headline. A percentage like 99.7 can mean different things depending on what is being counted. It can describe confidence that a signal exists in the data, meaning the measurement is unlikely to be random noise. It can describe confidence that a particular model fits better than alternatives, given the assumptions built into that model. It cannot by itself prove biology, because biology is not a single parameter that rises cleanly from a spectrum. Life is a process, and processes can share outputs with non-living chemistry. So we need to separate two kinds of confidence. There is confidence in detection, meaning the dip in starlight is truly there, repeatable, and not an artifact of the instrument. There is confidence in interpretation, meaning the dip implies a planet, an atmosphere, and specific chemistry that we have identified correctly. The first can be high, while the second remains fragile, because interpretation is where physics meets ambiguity. A clean shadow can still lead to a messy story. This documentary follows the chain that turns a dimming into a world, and it does not skip the weak links. It starts with photons and ends with philosophy, because the last step is not technical but human. It moves from spectra to chemistry, from chemistry to climate, from climate to habitability, and then to biosignatures. Then it asks the hardest step, whether habitability ever becomes evidence of life, or whether it remains a mirror for our hopes. Each stage adds inference, and inference is powerful, but it is also vulnerable. The universe is full of false positives, and astronomy has learned that lesson repeatedly. Signals can be made by instruments, by stellar activity, by data reduction choices, and by wishful thinking that quietly shapes which model feels reasonable. Detectors have quirks, telescopes breathe thermally, and pipelines must correct for effects that are real but hard to see directly. Planets can be missized if the star's radius is wrong, and atmospheres can be misread if the star's spectrum is not modelled well. Even on Earth, a single gas rarely tells a single story because context is what turns chemistry into meaning. History is crowded with premature announcements that later shrank under scrutiny. Canals on Mars became optical illusion and cultural momentum, reinforced by drawings that turned ambiguity into architecture. Meteorites that seemed biological became chemistry and contamination, as laboratories learned how easily Earth can imprint its own signature. Exoplanet atmospheres have produced headlines that later dissolved into noise and systematics, because early data often sits at the edge of what an instrument can reliably separate. The pattern is familiar. First excitement, then reanalysis, then the slower work of consensus. And still, some cases feel different, because the tools have changed. The James Webb Space Telescope was built to make the invisible readable, and its design is tuned for faint, precise measurements. Webb sees in infrared, where many molecules leave strong fingerprints that are muted or invisible in visible light. Webb is stable enough to measure tiny changes over long transits, holding its pointing and thermal environment steady. Webb is sensitive enough to treat starlight as a laboratory beam, turning a distant star into a backlight for chemistry. In visuals, Webb is not a romantic rocket, but a careful machine. Gold mirrors, black sunshield, and a cold, quiet observing posture. It does not fly to K22 or Routine B, and it does not photograph continents because the planet is far too small and too close to its star in angular terms. Instead, Webb watches the star and measures how the planet's atmosphere filters light as the planet passes in front. During a transit, a thin ring of atmosphere becomes a lens and a sieve, absorbing some wavelengths and letting others through. The result is a transmission spectrum, a barcode of missing light that we can compare to molecular physics. That barcode is where the story becomes dangerous, because it invites interpretation with high stakes. A spectrum can suggest water vapor, methane, carbon dioxide, or other gases whose absorption bands sit in the infrared like familiar notes in a chord. It can also be shaped by clouds, hazes, temperature gradients, and the star itself, which may have spots and faculae that change the apparent baseline. The same data can support multiple atmospheric models, and model choice can steer conclusions without anyone intending to mislead. Retrieval, the statistical process of inferring atmospheric composition from spectra, is powerful, but it is only as honest as its assumptions. K2-18b is described as a warm world, with estimates around 120 degrees Fahrenheit. That number is not a thermometer reading taken at the surface, because we do not know the surface, or even whether there is one in the familiar sense. It is a derived equilibrium range with assumptions, a balance between incoming starlight and outgoing heat. It depends on the star's output, the planet's reflectivity, and how heat moves through an atmosphere, including winds and possible greenhouse trapping. Warm does not mean Earth-like, but it keeps the door open because temperature influences chemistry, clouds, and the stability of volatile compounds. The unsettling part is the suggestion that the chemistry may not be static. Some interpretations describe an atmosphere that appears to pulse, in ways consistent with active processes, meaning the spectral features seem to change between observations. In popular retellings, that pulse becomes a heartbeat, a metaphor that lands because it feels alive. In careful science, it becomes a question about variability, retrieval uncertainty, and competing explanations, including whether the star changed or the instrument's systematics shifted. If a signal moves, the first task is to prove it moved in the sky, not in the pipeline. If certain gases appear together, the combination can be harder to explain without continual replenishment. Chemical systems tend toward equilibrium, and equilibrium is a kind of silence, where reactive species disappear unless something keeps making them. On Earth, biology is one way to maintain chemical imbalance, because life uses energy to build and release molecules that would otherwise not persist. But geology can also drive imbalance, through volcanism, serpentinization, and interactions between rock and water that generate reduced gases. Photochemistry can mimic it as well, as ultraviolet light breaks molecules apart and recombines them into surprising products. The central mystery is whether K2-18b shows a pattern that resists non-living explanations. That resistance is not a feeling, it is a comparison. Can we construct plausible abiotic pathways that produce the same spectral features under the planet's likely conditions? If we can, then the signal is interesting but not decisive, because nature is inventive without being alive. If we cannot, then the burden shifts, and biology becomes less like a wish and more like a candidate mechanism. Yet even then, the question remains, are we missing an abiotic pathway we have not yet imagined? The 99.7% framing tries to compress that uncertainty into a single headline number, and compression always loses texture. It suggests that, after accounting for noise and alternatives, life is the most likely cause, and that the case is nearly closed. But likelihood depends on what alternatives were included and how priors were chosen, and priors are where assumptions hide. A high percentage can reflect a narrow model space rather than a broad truth, especially if the models tested do not represent the full diversity of planetary chemistry. The number may be mathematically correct within its framework, while still being fragile in the real universe. So we must ask what the number actually measures, because the same percentage can be used to imply different levels of certainty. Is it a detection significance for a molecule in the spectrum, meaning the feature rises above noise at a certain sigma level? Is it a confidence level that the atmosphere contains a specific compound, given a set of retrieval choices and cloud assumptions? Is it a Bayesian probability that a biological model outperforms abiotic ones, given a particular library of scenarios? Each interpretation carries different weight, and each can be overstated when translated into everyday language. The stakes are not only scientific, they are cultural, because claims about life travel differently than claims about temperature. A confirmed living world would reorder our sense of rarity and belonging, and it would force new questions about how often chemistry becomes biology. It would change how we think about evolution, intelligence, and the future of exploration, because it would imply that life is not a singular accident. It would also test how society handles uncertainty, because the first claim will be amplified before it is settled. In that gap between announcement and verification, narratives grow faster than evidence. That amplification creates pressure on researchers and on instruments, even when everyone tries to be disciplined. Every new dataset becomes a referendum on the original claim, and every reanalysis becomes a battle over methods, assumptions, and credibility. Teams may choose different stellar models, different noise treatments, or different priors, and they can reach different conclusions from the same photons. When the subject is life beyond Earth, skepticism is not cynicism, it is the price of reliability. Yet it must be paired with curiosity, or it becomes a wall. At the same time, excessive caution can become its own bias, because fear of being wrong can quietly raise the bar beyond what any remote measurement can meet. If the evidence is strong, delaying the conclusion does not make it safer, only slower, and science is allowed to be provisional. The challenge is to build a standard that is strict enough to survive history, including the history of our own mistakes. The standard must also be realistic enough that discovery remains possible, even when the data is inherently indirect. K218b forces that balance because it is defined by inference, and inference is both the triumph and the limitation of exoplanet science. We do not touch it, sample it, or watch it weather in real time, because the system is too distant and too small. We infer its size from the depth of a transit, which itself depends on how well we know the star's radius. We infer its atmosphere from missing wavelengths, which depends on clouds, temperature, and the star's spectrum. We infer its temperature from energy balance, then infer chemistry from a few hours of filtered starlight, and then, most precariously, we infer biology from chemistry. This is why the opening shadow matters, because it is the first link in a chain of reasoning, and every link can bend. A fractional dip is small, but it is also repeatable, and repeatability is the foundation of measurement. Yet the chain is also how astronomy works at all, because distance forces us to become experts in inference. The method has already found thousands of planets and mapped atmospheres that were once unimaginable, including worlds hotter than molten rock and colder than liquid nitrogen. The question is whether it can now cross the final boundary, from atmosphere to activity, from activity to life. For K218b, the boundary is not just detection, it is interpretation under uncertainty, where the same spectrum can tell multiple stories. It is the difference between a molecule being present and a process being alive, because molecules do not carry labels that say who made them. It is the difference between a spectrum that fits a model and a world that fits a story, and stories are where humans become careless. It is the difference between excitement and evidence, and the gap between them is where most errors are born. We will treat the 99.7% chance of life as a hypothesis, not a conclusion, and we will keep the hypothesis tethered to what was actually measured. We will trace where the number comes from, what it assumes, and what it leaves out, because omissions are often more important than claims. We will ask what would lower it, what would raise it, and what would make it irrelevant, because some new data can change the question entirely. We will also ask what kind of proof is even possible from 120 light-years away, when our best tool is still a spectrum and a model. The path forward begins with how Webb reads atmospheres. It begins with the physics of light, the geometry of transits, and the way molecules carve patterns into infrared, each band a consequence of quantum energy levels. If we can understand the method, we can judge the claim, and we can see where uncertainty enters. If we can judge the claim, we can decide what it would take to call this a living world, and what would count as a false alarm. The next step is not a proclamation, but a mechanism, how a planet's shadow becomes a spectrum, and how a spectrum becomes a chemical inventory. Next, we start with the simplest question. How does a planet's shadow become a spectrum, and how does a spectrum become a chemical inventory? The shadow in Leo was only the first clue, because shadows can carry air, thin, reluctant air that still leaves fingerprints. When K2-18b crosses its star, the planet blocks most light completely, and the transit looks like a clean bite taken from a bright disk. But a narrow ring at the edge stays translucent, and starlight skims through it at a shallow angle. In that grazing path, photons travel through far more atmosphere than they would in a straight vertical drop. The geometry turns a simple eclipse into a long curved laboratory tube, and the star becomes the backlight. That edge is the atmospheric limb, a crescent of low-pressure gas wrapped around a world we cannot resolve. In silhouette, it is not a line, but a thickness, an annulus whose effective height depends on temperature, gravity, and composition. Physicists call that characteristic thickness the scale height, and it grows when gas is warm and light. It shrinks when gravity is strong, or when the mean molecular weight is heavy, making the limb harder to see. The light that survives is not the same light that entered, because the atmosphere filters it in wavelength-specific ways. Molecules absorb specific colours, leaving narrow deficits that physics can predict with uncomfortable precision. Even atoms and ions can contribute, though in this chapter the story stays with molecules and their richer patterns. Transmission spectroscopy is the name of this trick, and it turns a transit into a chemical experiment performed at interstellar distance. The idea is older than exoplanets, because astronomers use the same logic to study Earth's air during lunar eclipses. Now the geometry is reversed, and the planet is the filter instead of our own sky. We do not see clouds or continents, because the planet remains a single unresolved point blended with its star. Instead, we measure how the transit depth changes with wavelength, and then infer what caused it. The transit depth is basically a ratio, how much starlight is missing compared to the star's normal brightness. If the missing fraction changes with colour, something in the planet's limb is responsible, at least in principle. At some wavelengths, the planet looks slightly larger, because the atmosphere is more opaque there and blocks extra light. At other wavelengths, it looks smaller, because the gas is transparent and the limb becomes effectively thinner. The difference is tiny, often tens to hundreds of parts per million, which is like noticing a few extra grains of sand vanish from a stadium of light. Another way to picture it is a coin whose edge grows by a hair's breadth, depending on which colour you shine behind it. That scale is why exoplanet atmospheres were once a dream, and why stable space telescopes changed the rules. The entire method lives on the edge of what instruments can hold steady, where tiny drifts can masquerade as alien chemistry. The spectrum is not a picture of the planet, it is a pattern of missing photons, an absence with structure. Each missing band corresponds to quantum transitions in a molecule, where rotational and vibrational energy levels accept only certain photon energies. In plain language, molecules can only absorb very specific colours, and they do it repeatedly like a signature. The pattern is a barcode, but the scanner is a telescope more than 100 light-years away. The ink in that barcode is not pigment, but probability, because absorption depends on temperature, pressure, and how many molecules sit along the path. Pressure matters because collisions smear lines into wider shapes, and higher altitude gas leaves narrower, cleaner features. To visualize it, imagine a bright star as a white stage light, and the planet as a dark coin passing in front. Around the coin is a thin halo, and through that halo the stage light leaks, dimmed and tinted by the chemistry. The halo is not uniform because the terminator is where day meets night, and winds can pile gases differently. The path length through the limb is long, so even trace gases can matter if their absorption is strong. A few parts per million of a reactive molecule can still carve a detectable notch, if the line strengths are favourable. This is why a planet's atmosphere can announce itself even when it's only a tiny fraction of the planet's mass. Infrared is where this method becomes powerful, because many molecules speak loudest there, almost as if they were designed for it. Water vapour has strong bands across near-infrared wavelengths, and those bands are broad enough to be detectable even with modest resolution. Carbon dioxide, methane, ammonia, and complex organics also imprint distinctive infrared features, often at different wavelengths that help separate them. In the infrared, molecules are vibrating and rotating in ways that couple strongly to photons, producing families of lines that cluster into recognizable bands. In visible light, many of those same molecules are comparatively quiet, and their signatures can be weak or hidden. Visible light can miss or weaken these signatures, especially for cooler planets and hazy atmospheres where scattering dominates. Small particles can rarely scatter blue light, or larger aerosols can flatten the spectrum into something almost featureless. Infrared photons also probe different altitudes, because absorption strength varies with wavelength and pressure broadening changes line shapes. Some wavelengths get absorbed high up, while others slip deeper before they are stopped. That vertical sensitivity is subtle, but it matters, because temperature and clouds change with height. Webb was built around this advantage, with instruments tuned for stable infrared spectra and careful control of thermal behavior. Its sunshield is not just engineering theatre, it is what keeps the telescope quiet enough to hear faint molecular whispers. There is also a historical reason infrared became the battleground for atmosphere claims. Early exoplanet spectroscopy leaned on the few wavelengths accessible to earlier telescopes, and many results lived near the edge of credibility. In the 2000s and 2010s, observers wrestled with warm optics, changing detector baselines, and stars that refused to behave like constant bulbs. As methods matured, the community learned to distrust single-band surprises, especially when stars were active and instruments were warm. Infrared from space reduces some of those problems, though it introduces its own discipline and its own kinds of noise. Webb arrived into that history as both a promise and a test. Could we finally measure atmospheres as a routine craft, not a heroic exception? Webb does not use one sensor for everything, and that matters for trust, because different hardware fails in different ways. NIRISS can capture broad near-infrared spectra optimized for transits, where stability and wide coverage help map the overall shape. NIRSpec can resolve features more finely across key near-infrared bands, separating blended absorption into more interpretable structure. MIRI extends the reach into mid-infrared, where other molecules become easier to separate, and where thermal emission physics becomes more relevant. Each instrument has different detectors, optics, and calibration behavior, and each carries its own systematics. When multiple instruments agree, it is like hearing the same melody played on different strings, less likely to be a trick of one instrument's wood. In a documentary frame, you can picture the observatory as a quiet machine at L2, its gold mirrors holding a cold, steady gaze. The spacecraft sits in perpetual twilight, with Earth and Sun held on the same side so the sunshield can do its work. Light enters, gets split, dispersed, and recorded as a rainbow stretched across pixels. The rainbow is not decorative. It is a measurement grid, where each column corresponds to a wavelength channel. During transit, the entire rainbow dims, but it does not dim evenly. The art is to measure that unevenness without confusing it for the telescope's own breathing. Agreement across modes can strengthen a claim, while disagreement can expose a hidden bias that no one meant to introduce. If NIRISS sees a broad water-like dip, and NIRSpec sees matching structure at higher detail, the story gains weight. If MIRI later finds consistent behavior where mid-infrared bands should appear, the case becomes harder to dismiss. But if one instrument sees a feature and another does not, the first question is not what exotic chemistry, but what changed. That question can be about the planet, yet it is often about the star or the instrument. The harsh discipline of this field is that every exciting feature must survive being doubted from multiple angles. The measurement begins as raw counts, not chemistry, and that detail keeps the narration honest. A detector records how many photons arrive in each wavelength channel over time, producing a time series for every slice of the spectrum. During transit, the counts drop, and the wavelength dependence of that drop is the signal we chase. Before any molecule is named, the data look like slightly different light curves stacked side by side. The atmosphere is encoded as tiny differences in the depth and shape of those curves. In the control room, those curves are the first moment of suspense, because they are where the universe either speaks or stays quiet. Signal to noise becomes a character, because the atmosphere's imprint is smaller than the planet's shadow. Photon noise is fundamental, because light arrives in discrete packets, and counting packets has unavoidable statistical scatter. Fainter stars and narrower wavelength bins reduce counts and raise uncertainty, which is why observers balance resolution against precision. If you split the light too finely, Each channel becomes starved, and the spectrum turns into static. If you keep channels too broad, you smear out the very features you hope to identify. The compromise is never purely technical, because it shapes what kinds of atmospheres you can even test. There is a simple intuition behind the math. If you collect 4 times as many photons, random noise drops by about a factor of 2. That is why integration time matters, and why large mirrors matter, and why stable detectors matter. Yet the atmosphere signal does not scale up with time the way the star's brightness does. The signal is a fractional change, and the fraction is fixed by physics, so you win by shrinking uncertainty. Every part per million you shave off is purchased with careful observing and careful reduction. Noise is not only random, it is structured, and structured noise can mimic a spectrum with cruel plausibility. The telescope's pointing can drift slightly, moving the spectrum across detector pixels that are not perfectly identical. The detector response can change with time, creating trends that look like astrophysics if you're not cautious. Even tiny thermal changes can shift focus or throughput, and those shifts can correlate with wavelength. When you are measuring tens of parts per million, the instrument's personality becomes part of the plot. The danger is not obvious spikes, but smooth, believable curves that look like real absorption. Integration time fights randomness, but it cannot automatically defeat systematics, because systematics do not average down like coin flips. Longer observations collect more photons and average downshot noise, which is the comforting part of statistics. Yet if the instrument drifts, longer time can also accumulate a larger false pattern that looks smooth and convincing. In other words, you can integrate your way into a mistake if you do not model the drift. Precision is not the same as accuracy, and exoplanet spectroscopy demands both. That is why repeated transits matter more than a single beautiful event, even when the first spectrum looks dramatic. Each transit is another chance to separate repeatable features from one-off quirks, because the planet repeats its geometry with clockwork regularity. If a feature appears at the same wavelength across visits, confidence rises, and the temptation to overinterpret falls. Repetition also lets observers test different instrument settings and different extraction choices. A robust signal should survive those changes, even if its error bars shift. But repetition introduces another complication, because the star is not a steady lamp, and it never promised to be. Stars have spots that are cooler and darker than the surrounding surface, and those spots can cover significant fractions of the disk. They have faculae that are hotter and brighter, often clustered around magnetic regions. Both spots and faculae evolve between transits, and they rotate in and out of view as the star spins. When the star changes, the baseline spectrum changes, and the planet's atmosphere can be blamed for what the star did. A planet transiting a spotted star does not sample the same stellar spectrum every time, even if the orbit is perfectly periodic. If unocculted spots cover part of the star, the baseline light changes colour, because cooler regions emit relatively less blue and more red. That colour shift can masquerade as atmospheric absorption in the planet, especially as a broad slope across wavelengths. If the planet crosses a spot, the transit can look shallower temporarily, because the planet is blocking a dimmer patch. Those anomalies are not just nuisances, they are signals of stellar surface structure. In a visual sequence, you can almost see the planet's silhouette sliding over a mottled, living photosphere, like a bead crossing marbled glass. Flares add urgency because they can inject sudden brightness changes and spectral distortions on timescales comparable to a transit. Even small flares can alter the light curve shape and the inferred transit depth, particularly in wavelength channels sensitive to the flare's hot continuum. For active stars, stellar contamination can dominate the error budget, and it can do so invisibly if you only look at the final spectrum. A flare that happens outside the transit can still shift the baseline and bias the depth. The star's magnetic weather becomes part of the planet's supposed chemistry. To handle this, observers model the star as carefully as the planet, because the measurement is fundamentally a star plus planet system. They monitor out-of-transit variability to estimate spot coverage and evolution, often using simultaneous photometry or long-term light curves. They test whether the spectrum can be explained by stellar heterogeneity alone, without invoking any atmospheric features. In practice, this means building models where the star has multiple temperature components and asking how that composite spectrum would change the apparent transit depth. It is not glamorous work, but it is the work that keeps claims from collapsing. They also compare different wavelength ranges because star spots and molecules scale differently with wavelength, in ways that can be diagnostic. A spot-induced slope can appear broad and smooth across wavelengths, like a gentle tilt rather than a set of notches. Molecular absorption tends to produce localized bands at known positions, sometimes with repeated structure across adjacent channels. If you see a feature exactly where water should absorb, and you see it with the right shape, that is meaningful. If you see a smooth drift that could be temperature contrast on the star, that is a warning. Instrument systematics are the other adversary, because Webb is precise enough to reveal its own habits, and those habits can be subtle. Detectors can show ramp effects, where sensitivity changes during an exposure sequence as charge traps fill and release. Thermal breathing can shift focus and throughput across an observation, even in the cold stability of space. Pointing jitter can couple with pixel-to-pixel sensitivity differences and create false spectral structure. Background subtraction can introduce wavelength-dependent offsets if the scene changes, and in the infrared, the background has its own behavior. Even the zodiacal light and the telescope's own faint glow can matter, because dark in the infrared is never perfectly dark. Even the choice of extraction aperture can tilt the spectrum, because you are deciding how much of the point spread function to include at each wavelength. If the spectrum shifts slightly, a fixed aperture can lose light differently across channels. If you use a variable aperture, you may introduce other correlations with time. These are not errors in the moral sense. They are consequences of measuring at the limit. The point is that the data reduction is part of the experiment, not a clerical step after the fact. This is why calibration pipelines are not a formality. They are part of the measurement, and they encode years of instrument characterization. Raw data is corrected for dark current, flat fields, and nonlinearity, because detectors do not respond perfectly to light. Cosmic rays are identified and removed, because space is not a clean laboratory. Time-dependent trends are modeled, and residuals are inspected for correlated noise, because correlation is where false confidence hides. When the residuals look random, the observer breathes easier, though never completely. Independent reductions act as safeguards against a single team's assumptions, and this practice has deep roots in the history of precision astronomy. Different groups may choose different detrending functions and different priors, and they may treat outliers differently. One team might model systematics with a polynomial in time, while another uses a physically motivated detector model. If multiple pipelines converge on similar features, the result becomes harder to dismiss as an artifact of taste. If pipelines disagree, the disagreement is itself information about what the data can honestly support. In a field built on tiny differences, humility is not a personality trait, it is a method. Still, a spectrum is not a direct list of gases, because temperature and clouds reshape it, sometimes dramatically. A high cloud deck can mute absorption by blocking deeper layers, turning a potentially rich spectrum into a flatter line. Hazes can add a smooth opacity that hides narrow features, especially at shorter wavelengths where scattering is strong. Temperature affects the atmospheric scale height, which sets how tall the absorbing annulus effectively is. Higher temperature means a puffier atmosphere and deeper features, while higher gravity squeezes the same gas into a thinner shell. In retrieval plots, these effects can trade places, creating degeneracies that look like certainty if you forget what is being assumed. There is also chemistry, which is not just what is there, but what survives there. Molecules can be broken apart by ultraviolet light, and they can recombine into other species depending on available atoms. The terminator region is a mixing zone, where dayside photochemistry meets nightside cooling. Even if the bulk composition is stable, the limb can be layered, with different molecules dominating at different altitudes. Transmission spectroscopy is most sensitive to those higher layers, because the slant path amplifies their influence. That sensitivity is a gift and a trap, because the upper atmosphere can be the most variable part of the system. Retrieval is the statistical step that tries to reverse this compression, turning a measured pattern into a set of plausible atmospheres. A forward model generates spectra for assumed compositions, temperatures, and clouds, and it predicts what the telescope would see. The retrieval searches parameter space and returns probabilities for what fits best, usually by comparing many models to the data. In plain language, it is a disciplined guessing game, where each guess is constrained by physics and by the instrument's response. The output is not a single answer, but a distribution of answers with uncertainties. the most honest retrievals also return correlations, showing which parameters are entangled and which ones the data truly constrain. But retrieval is only as honest as its model family, and that is where caution begins to feel like a moral obligation. If the model assumes a certain cloud type, it may force chemistry to compensate for missing opacity. If it ignores stellar contamination, it may invent molecules to explain slopes that belong to star spots. If it assumes the atmosphere is well mixed, it may mislayered structures that could change the interpretation. These are not trivial choices, because different assumptions can shift a detection into a non-detection without changing the raw photons. So we need to separate two kinds of confidence. One is confidence that a feature exists in the data beyond noise, meaning the telescope truly measured a repeatable wavelength-dependent signal. The other is confidence that the feature is correctly attributed to a specific molecule and planet process, meaning the story we tell matches reality. The first kind of confidence is about statistics and systematics, and it can be strengthened with more data. The second kind is about degeneracy, because different atmospheres can produce similar spectra. Confusing these two is how headlines outrun evidence. This is where the headline number enters, because 99.7% can mean several things, and the phrasing matters. It can be a detection significance, roughly equivalent to about 3 sigma, which is a statement about how often noise alone would mimic the observed feature. It can be a posterior probability within a chosen retrieval framework, which is a statement about model comparison given priors. Those are not the same claim, even if they sound similar in casual speech. The number is not a stamp of truth, it is a summary of a specific statistical question. 3 sigma is not a magic threshold, it is a convention about how rarely noise mimics a signal under an assumed null model. It says the feature is unlikely if the data were pure noise, which is important but limited. It does not say the interpretation is unique, or that life is implied, or even that the star is innocent. In fields that live at the edge of detectability, 3 sigma can be a starting point rather than a finish line. The community has learned, sometimes painfully, that significance can be inflated by unrecognized systematics. A posterior probability can sound stronger, but it depends on priors and model choices that are often invisible in a headline. If the model set is narrow, the posterior can be artificially decisive, because the algorithm was never allowed to consider alternatives. If the priors favour certain molecules, the retrieval can lean toward them even when data are ambiguous. Science prefers cautious language because the universe can be broader than our libraries, and because nature does not care what we expected. The most responsible result is often a range of possibilities with clear caveats. With that caution in place, the suspense returns to what Webb reportedly saw in K218b and why it caught attention beyond a single molecule. Analyses described a warm atmosphere with absorption patterns consistent with water vapour, appearing as bands where infrared light should be eaten away. They also suggested carbon-bearing chemistry that could include methane or related species, though the exact identification depends on model details. In practice, those claims rest on whether the observed notches align with expected band shapes, not just whether a line appears somewhere convenient. The phrasing "consistent with" is doing work here, because it acknowledges that multiple explanations can overlap. Still, even consistency is meaningful when the data are this delicate. The intrigue is not one molecule, it is the possibility of chemical disequilibrium, an atmosphere that looks like it is being actively maintained. In a stable atmosphere, reactive gases tend to destroy each other over time, moving toward chemical equilibrium. If they persist together, something must replenish them continuously, or the atmosphere must be structured in a way that keeps them apart. Disequilibrium is not a single signature, but a tension between what chemistry wants and what the spectrum suggests. That tension is what makes scientists lean forward. It is also what forces the next questions. What energy sources exist, what reservoirs exist, and what timescales are realistic. On Earth, biology is one replenishment engine, but it is not the only one, and that distinction protects us from wishful thinking. Volcanism can inject reduced gases and aerosols, altering atmospheric composition on short timescales. Water rock reactions can generate hydrogen and methane under certain conditions, especially where minerals meet liquid water and heat. Impacts can also transiently change chemistry, though those events are episodic and often violent. The point is not to dismiss life, but to respect the number of ways a planet can surprise us. Every non-living pathway you can name becomes a control experiment you must mentally run. Photochemistry can also create surprising mixtures, especially under different ultraviolet environments than the Sun provides. A star's spectrum can drive pathways that do not occur on Earth, producing hazes or destroying certain molecules faster. The balance depends on UV flux, atmospheric shielding, and circulation that moves gases between day and night. So disequilibrium is a clue, not a verdict, until context narrows the options. The same set of molecules can mean different things on different worlds because the surrounding physics changes the story. Some reports added a more dramatic layer, describing chemistry that seemed to change between transits, as if the atmosphere refused to sit still. In careful terms, the spectral features appeared variable beyond expected uncertainties, which is a cautious way of saying the data did not line up perfectly. In popular terms, the atmosphere seemed to pulse, brightening and dimming in specific bands like a slow heartbeat. That image is powerful, but it must be earned, because variability is where systematics and astrophysics can easily tangle. When you compare visits separated by weeks or months, you're comparing different instrument states and different stellar moods. Variability has many non-living explanations that must be tested first, and the list is long because atmospheres are weather machines. Weather can move clouds and change the effective altitude of absorption, making features appear stronger or weaker without changing composition. Patchy haze can drift across the terminator and alter the spectrum's contrast, especially if winds redistribute aerosols. Temperature changes can shift scale height and broaden features, even without changing the underlying molecular abundances. Photochemical production can vary with stellar activity and flare history, changing the upper atmosphere where transmission is most sensitive. Even a small change in cloud-top pressure can translate into a measurable change in apparent planet radius at specific wavelengths. Instrument systematics can also mimic variability if conditions differed between visits, which is why observers obsess over consistency checks. A different pointing jitter pattern can change how light falls on pixels, and that can shift apparent depths in wavelength-dependent ways. A different detector ramp behavior can imprint a slope that looks like changing haze. Even subtle differences in background, particularly in the infrared, can alter the extracted spectrum. The danger is not that the data are wrong, but that the interpretation can be too eager. Yet variability also keeps the life question alive, because biology is inherently dynamic, and because living planets rarely sit in perfect equilibrium. A biosphere can modulate gases seasonally or episodically, depending on energy input and circulation. On Earth, biological activity responds to sunlight, nutrients, and temperature, and those responses have rhythms. If a pattern repeats with orbital phase, it becomes a stronger target, because repetition tied to the planet's clock is harder to blame on random noise. The idea is not that variability proves life, but that it invites stricter tests. It also invites a quieter question. If a world is alive, would it look steady from far away, or would it look restless? The credible path is to treat variability as a hypothesis to be stress-tested, not a conclusion to be celebrated. Do the same features appear in different instruments and different reductions, even when you change extraction choices and detrending models? Do they correlate with stellar indicators, like spot-driven brightness changes or flare signatures, which would suggest contamination? Do they correlate with detector state and pointing behavior, which would suggest systematics? If the variability survives those comparisons, it becomes a puzzle worth deeper investment. If the spectrum survives those tests, then the signal becomes more than a curiosity, and it begins to look like a measurement with a future. It becomes a target that can be refined with more transits and broader wavelength coverage, narrowing degeneracies by design. It becomes a case where uncertainty shrinks because the observing program is built to shrink it, not because we hope the next plot looks cleaner. Over time, multiple visits can map whether the atmosphere is stable, patchy, or genuinely changing. The story can move from "is there a feature?" to "what kind of atmosphere behaves like this?" The path forward begins with how Webb reads atmospheres, but it cannot end there, because chemistry alone does not define a living world. A spectrum can suggest water and carbon chemistry, yet habitability depends on energy and environment, on whether the planet can maintain conditions that allow complex processes to persist. If the signal is real, the next question is whether the planet can host stable conditions rather than brief chemical fireworks. That question pulls us outward to the star's luminosity and inward to the planet's gravity and heat transport. It also pulls us toward time because stability is a long game, so we descend from light into climate, orbit, and energy balance. We move from what the atmosphere might contain to what the world might be like, including how heat is redistributed from day to night. We ask what it would take to keep water vapour present, and what pressures and temperatures would make the limb look the way it does. We ask how clouds could form and where they would sit, because clouds are both climate actors and spectral masks. And we ask what it would take to turn a 3 sigma whisper into a durable claim. The central question remains unchanged, even as the method becomes clearer and the caveats sharpen. Did Webb truly detect a living world on K2-18b, or only a clever illusion of physics, an overlap of stellar complexity, instrument behaviour and statistical enthusiasm? The next chapter tests the environment that would have to support the chemistry we think we saw, because atmosphere claims ultimately live or die in planetary context. If the world cannot plausibly sustain the conditions implied by the spectrum must be reinterpreted. And if it can, the mystery deepens, because the universe has just offered us a more intimate kind of evidence. We descend from spectra into the harder question of environment, where numbers stop being labels and start being physics. K2-18b's habitability claim begins with one number, around 120 degrees Fahrenheit, and it lands like a verdict. That headline sounds familiar, like a hot summer day on Earth when asphalt shimmers and air feels heavy. Yet the first task is defining what that temperature actually means, because exoplanet temperatures are often proxies rather than readings. On distant worlds, we rarely measure a surface directly. What we usually measure is light, filtered through geometry and chemistry. In exoplanet work, temperature can refer to equilibrium temperature, which is a simplified accounting of absorbed and emitted energy. It can refer to brightness temperature inferred from emitted infrared light, which is tied to what a telescope actually senses. It can refer to a modelled surface or cloud-top temperature, which is an output of assumptions layered on assumptions. Those definitions are not interchangeable, and they can diverge by tens to hundreds of degrees once atmospheres become thick or cloudy. A planet can have a mild equilibrium temperature and a lethal surface, or a hot equilibrium temperature and habitable niches hidden in circulation patterns. The gap between those outcomes is not rhetoric. It is radiative transfer, fluid dynamics, and chemistry. Equilibrium temperature is a bookkeeping estimate used because it is quick, comparable, and often the only thing you can compute early. It assumes incoming starlight is balanced by outgoing thermal radiation, with a chosen albedo and a simplified heat redistribution between day and night. In many papers, the parameter is written like a clean answer, even though it is really a controlled thought experiment. In plain terms, it treats the planet like a sphere with a paint colour and a radiator, then asks what temperature makes the math close. It ignores weather, ignores vertical structure, and ignores the way real gases absorb in bands rather than smoothly. It also hides a crucial choice, whether the day side re-radiates quickly, or whether winds smear heat around the globe. Brightness temperature is what the telescope infers from the planet's glow at specific wavelengths, and it is always tied to an altitude. It samples certain layers where the atmosphere becomes transparent at those wavelengths, and it can be biased by clouds, composition, and temperature inversions. In other words, it is a temperature of an emitting layer, not a guarantee about what lies beneath. A temperature inversion is a subtle trap for intuition, because it flips the normal expectation that higher means colder. If a layer is warmed by absorbing starlight or chemical heating, the spectrum can make a planet look hotter or cooler than its surface. On Earth, inversions can trap smog in valleys, but on exoplanets they can rewrite the entire interpretation of a band. Modelled surface temperature is the most speculative, even when it is presented with confident precision. It depends on greenhouse strength, atmospheric pressure, circulation, and whether there is even a solid surface to define as surface. The model must also decide how water behaves, how clouds form, and how efficiently heat is carried upward by convection. On some worlds, the surface might be an ocean, or a high-pressure ice lid, or a boundary deep inside a gas envelope. In those cases, the temperature we care about may be inaccessible to both light and inference. We can still speak about habitable conditions, but we must be honest about where those conditions could exist. So the 120-degree number is not a thermometer reading. It is a clue that must be placed inside an energy budget. Energy balance starts with the star, because the star is the furnace, and the planet is the thermostat. K2-18b orbits a small cool star in Leo, likely an M dwarf, and that changes the entire climate story. In the history of exoplanets, M-dwarfs became central not because they are ideal suns, but because their small size makes planets easier to detect. Visually, an M-dwarf is not a miniature sun with the brightness turned down, but a different kind of lamp. Its light is deeper red, its spectrum is crowded with molecular absorption, and its variability can be more dramatic than its calm appearance suggests. If the sun is a white-hot disk, an M-dwarf can look like a dim ember, steady in colour yet capable of sudden violence. A cooler star emits more of its energy in red and infrared light, shifting how a planet absorbs energy and where that energy is deposited. That shift matters for water vapour, for cloud particles, and for photochemistry driven by shorter wavelengths. It also matters for surface illumination, because what looks bright to human eyes is not the same as what heats an atmosphere. At the same total power, redder light penetrates deeper in some atmospheres and interacts differently with aerosols that would be bright under sunlight. The same planet can warm or cool depending on which wavelengths dominate, because scattering and absorption are wavelength dependent. A haze that would gleam under blue light can become nearly transparent under red, and the climate result can flip. This is one reason the habitable zone is not a simple ring drawn at a distance, even though it is often shown that way. The habitable zone depends on stellar colour, atmospheric composition, and feedbacks that can amplify small differences. Historically, the idea began as a rough guide for liquid water, then matured into a field of competing models with different cloud and humidity assumptions. The orbital distance sets the irradiance, the power per square metre arriving at the top of the atmosphere. Irradiance rises sharply as a planet moves inward, and K2 and 18b is close enough that small distance errors matter. Even a modest change in stellar luminosity estimates can shift the energy budget enough to change whether clouds stabilise or collapse. Distance also sets the rhythm of seasons, or the lack of them, because a close orbit can erase long seasonal cycles. When an orbit is tight, the star fills more of the sky, and the planet's climate becomes a constant negotiation with a nearby heat source. The year becomes short, and the atmosphere has less time to forget yesterday's heating pattern. From irradiance we subtract reflected light, and reflection is not a detail but a lever. Albedo is the fraction of starlight bounced back to space, and it is controlled by clouds, hazes, ice and surface type. On a world we cannot resolve, albedo is an invisible dial that still decides the outcome. On Earth, albedo is visible in satellite images where storms swirl bright white and oceans look like dark ink. On an exoplanet we rarely see that directly, yet the same physics decides whether energy is absorbed or rejected. A planet with a global cloud deck can behave like a mirror, even while its lower atmosphere cooks. A high albedo can keep a planet cooler than expected, even under strong starlight, because it returns energy before it becomes heat. A low albedo can turn a marginal world into a heat trap, because every photon that stays becomes part of the thermal load. The difference between a pale world and a dark one can be the difference between stable oceans and a runaway greenhouse. Then comes the greenhouse effect, the atmosphere's ability to block outgoing infrared heat while remaining transparent to much of the incoming light. Greenhouse warming depends on which gases absorb, how pressure broadens their lines, and where clouds sit relative to the infrared emitting layers. The greenhouse effect is not a single knob, it is a network of overlapping absorption bands. Spectroscopically, greenhouse gases are not blankets in the everyday sense, but collections of quantized absorption bands. Molecules like water, carbon dioxide, methane and ammonia absorb at specific wavelengths, and pressure can smear those bands into wider, stronger barriers. That smearing happens because collisions perturb molecular energy levels, an invisible crowding that makes absorption more continuous. This is where comfortable numbers become dangerous, because equilibrium temperature can hide the vertical structure that controls surface conditions. A planet with an Earth-like equilibrium temperature can still be a Venus-like furnace if greenhouse trapping is strong and the infrared photosphere sits high. The infrared photosphere is simply the altitude where the atmosphere finally becomes transparent enough for heat to escape. The reverse can also happen, and it is equally important for K228b's story. A planet with a hot equilibrium estimate can be moderated by reflective clouds, efficient winds, or a high albedo haze layer that rejects starlight before it heats the lower atmosphere. A world can look overcooked on paper, yet harbour cooler layers where liquid water could persist. Clouds are the wild card because they can cool and warm at the same time, depending on altitude and particle properties. Low bright clouds reflect incoming light and cool the surface, while high, thin clouds can trap outgoing heat and warm the lower atmosphere. Even on Earth, small changes in cloud altitude can shift climate sensitivity in ways that still challenge models. If you could hover above such a world, you might see a bright day side like a pearl, then a darker band near the terminator where clouds thin. That visual contrast would not just be beauty, but the signature of energy moving through a fluid system. The boundary would look like weather frozen into geography, even though it is driven by circulation. Cloud composition matters as much as cloud height, because different condensates scatter and absorb different parts of the star's spectrum. Water clouds, sulfuric acid clouds, and hydrocarbon hazes each have different refractive indices, different particle sizes, and different infrared behavior. Particle size alone can shift a cloud from reflective white to a muted light-absorbing veil. Around a cool star, water clouds can behave differently than they do under sunlight because the incoming spectrum is shifted. The star's redder output can reduce the cooling power of some clouds, shifting the balance toward warming in ways that surprise Earth-based intuition. In models, the same cloud deck can either rescue a planet from overheating or fail to do so, depending on microphysics. Cloud feedback can create multiple stable climates at the same orbit, which is a quiet but profound idea. One state can be temperate and cloudy, another state can be hot and clear, and the planet can flip if conditions change. Climate becomes a landscape with more than one valley, and a planet can settle into different valleys depending on its history. That flip can be triggered by small changes in composition, or by slow changes in stellar output, or by internal outgassing that thickens the air. When we see a single snapshot spectrum, we may be catching one phase of a climate that has more than one resting place. The spectrum can be a portrait of a moment, not a biography. Atmospheric pressure is the plot twist that makes the same temperature mean different things, because pressure rewrites the phase diagram of water. Pressure controls boiling points, heat transport, and how thick the greenhouse blanket can become. It also controls how easily a planet's atmosphere can carry latent heat, the energy stored in water vapor. At low pressure, 120 degrees Fahrenheit can be irrelevant for life, even if it sounds merely hot. Water can boil away at much lower temperatures, and the surface can be dry even if the air feels warm. The planet can have water vapor overhead, yet never sustain stable puddles, lakes, or oceans. Low pressure also means less shielding from radiation and less capacity to move heat, so day-night contrasts sharpen. A thin atmosphere can make a planet's climate feel like a set of disconnected regions rather than one coupled system. In extreme cases, gases themselves can freeze out on the night side, thinning the atmosphere further. At high pressure, liquid water can persist at higher temperatures, and that changes the meaning of too hot. A dense atmosphere raises the boiling point, stabilizes warm oceans, and increases the capacity to move heat from the day side to the night side. High pressure can also suppress evaporation rates in complex ways, changing how clouds form and how storms behave. Pressure also changes the spectrum we measure, which matters because our evidence is spectral. Higher pressure broadens absorption lines and can hide composition details, while also increasing the scale of greenhouse warming by strengthening infrared opacity. The same pressure that makes oceans stable can make retrievals ambiguous. To evaluate pressure, we need the planet's gravity and size class, because pressure is weight per area. K2-18b's radius suggests it is larger than Earth, in the super-Earth to mini-Neptune range, and that range is not a minor label. It is the regime where exoplanet catalogues became crowded, and where nature refused to give us a single template. It is a fork in the story, because it points to different formation histories and different atmospheric outcomes. A super-Earth might have a rocky surface with a secondary atmosphere built from outgassing and impacts, while a mini-Neptune might have a deep hydrogen envelope and no accessible surface. Both can share similar radii, which is why radius alone can mislead. Radius alone cannot decide between those fates, because a puffy atmosphere can inflate a small core and mimic a larger planet. Mass is needed to estimate density, and density decides whether the planet is rock-dominated, water-rich, or gas-dominated. The lesson was learned repeatedly as radial velocity follow-up turned Earth-like candidates into something stranger. Historically, this is where exoplanet science learned humility, because early radius measurements created confident categories that later mass data complicated. The radius valley and the diversity of sub-Neptunes showed that small changes in mass and irradiation can produce very different atmospheres. The valley itself likely reflects atmospheric loss, a slow sculpting by stellar radiation over billions of years. If K218b is dense, gravity is stronger and the atmosphere is more compressed, which changes both climate and observability. Scale height shrinks, spectral features weaken, and the planet can still hold a substantial atmosphere that is harder to read. A compact atmosphere can be chemically rich, yet spectrally subtle. If K218b is low density, it may retain a thick hydrogen-rich envelope, which is a different world entirely. Hydrogen increases scale height and makes spectral features easier to detect, but it can also imply high pressures and a deep, hot interior. The atmosphere can behave like a vast insulating layer, with conditions changing dramatically over a few scale heights. A hydrogen-rich world can be warm at the top and crushing below, with temperatures rising as you descend into denser layers. Habitability then shifts from a surface question to a chemistry and clouds question, harder to test and easier to romanticize. The word habitable starts to mean somewhere in the column, not a place you could stand. An ocean world is another possibility, and it sits between rock and gas in a way that complicates simple labels. A planet can be water-rich with a global ocean over high-pressure ice layers, separating the ocean from rock and limiting nutrient cycling. In visuals, it is a blue-black sphere with no continents, the ocean unbroken except by storms. That separation matters for biology, because life needs more than water and warmth. It needs chemical gradients and access to elements that build complex molecules. On Earth, those gradients are refreshed by tectonics, volcanism, and water-rock reactions that feed cycles. The ocean is not just a habitat, it is a reactor connected to a restless crust. If the ocean is capped by high-pressure ice, the seafloor can be geochemically isolated, and the chemistry can become stagnant. A biosphere could exist, but productivity could be limited by nutrient bottlenecks and by reduced access to phosphorus and trace metals. The ocean might be vast, yet biologically quiet, alive in pockets, not roaring at planetary scale. If the planet is rocky with shallow oceans, water-rock interactions can supply energy and nutrients in a more direct way. That scenario supports more Earth-like pathways for microbial ecosystems, including hydrothermal systems that can run for long periods. In that case, the planet's warmth becomes less threatening and more like a steady engine. Now we return to the 120-degree claim and ask which layer it describes, because layers are the real setting of this story. If it is an equilibrium estimate, it says little about the surface, and it can be compatible with many climates. It is a first sketch, not a photograph. If it is a brightness temperature, it may describe a cloud deck or an emitting layer high in the atmosphere. In that case, the number is less about where life would live and more about where photons last interacted before escaping. The measurement becomes a map of transparency, drawn in infrared. A cloud top at 120 degrees can sit above a far hotter lower atmosphere, and that is not hypothetical. That is a familiar trick on Venus, where mild temperatures exist at high altitude above an extreme surface that can melt lead. The visual of Venus helps here. A bright, featureless globe, beautiful from afar, brutal at the ground. Venus is also a reminder that Earth-sized and Earth-like are not twins, even in our own solar system. Its albedo is high, its equilibrium temperature is not absurdly high, and yet its greenhouse effect dominates everything that matters at the ground. The cautionary tale is not that Venus is unique, but that atmospheres can overpower size. A surface at 120 degrees is not automatically fatal to life, even if it is beyond human comfort. Many Earth microbes tolerate higher temperatures, and warm oceans can be biologically active if chemistry and stability cooperate. The upper temperature limit for known life is high enough to make our discomfort a poor guide. The key is not a single peak temperature, but persistence and replenishment, because ecosystems need time. A planet that swings between extremes or loses water to space can be briefly warm and still sterile. Habitability is a long-term contract between climate and chemistry, not a weather report. The star's spectrum controls that long-term stability, and M-dwarfs complicate it with activity. Many M-dwarfs are magnetically active, with flares and ultraviolet bursts that reshape atmospheres and erode volatiles, especially early in the star's life. The paradox is that M-dwarfs live for trillions of years, yet their youth can be harsh enough to sterilize nearby worlds. Visually, a flare is a sudden brightening, a flash that would make the star's disk look like it has a wound of light. Physically, It is magnetic energy converted into radiation and particles, and it can bathe nearby planets in short wavelength photons. The planet's upper atmosphere can glow, expand, and leak under that assault. Ultraviolet light drives photochemistry, meaning it can break molecules and start reaction chains that would not occur otherwise. It can destroy methane and ammonia, produce hazes, and generate oxidants that change what gases can survive over long times. Those oxidants can also attack the very molecules we might hope to interpret as signs of life. Those reactions do not just change composition, they change climate, because composition sets infrared opacity. A haze that forms from photochemistry can cool a planet by reflecting light, or warm it by absorbing, depending on particle size and altitude. The same chemistry that sculpts the spectrum can also sculpt the temperature profile. UV also sets the surface radiation environment, which matters for any exposed biosphere. Without shielding, UV can sterilize exposed surfaces, pushing habitability underground, underwater, or into the twilight band where exposure is reduced. Even a shallow ocean can be a powerful shield, turning lethal radiation into harmless heat. An ozone-like shield is not guaranteed, and the word ozone can mislead by familiarity. Ozone on Earth depends on oxygen, and oxygen depends on sources that may be absent, intermittent, or ambiguous on other worlds. Even if oxygen exists, the balance between production and destruction can be tipped by stellar UV in ways that change the thickness of any protective layer. Even without ozone, other absorbers can provide protection, though they come with trade-offs. Hazes can block UV, and thick atmospheres can attenuate radiation, though they also complicate spectral interpretation by muting molecular features. Protection and detectability can be in tension, as if the planet must choose between safety and transparency. The same haze that protects life can hide it from Webb, which is the observational irony at the centre of this chapter. Aerosols flatten spectral features and reduce the contrast of molecular bands, making retrievals more degenerate and less decisive. A spectrum that looks smooth can be a sign of clouds, not a sign of simplicity. A hazy atmosphere can mimic a different composition, because a muted spectrum can be fit by multiple models. It can make water bands look weaker, make methane look absent, and push models toward incorrect conclusions that still match the data. In retrieval space, many solutions can sit on the same curve, and the data alone may not choose. Clear air versus hazy air changes everything, not just for detection but for climate inference. Clear air allows deeper probing and more confident molecule identification, while haze forces us to infer chemistry through partial muted fingerprints. The planet becomes a silhouette with hints, and the hints can be overinterpreted. This is why climate and spectroscopy are inseparable, even though they are often discussed as separate disciplines. The atmosphere that sets temperature also sets what Webb can detect, and the same cloud layer can both cool the planet and hide its gases. The climate model and the spectral model are really the same model viewed from different angles. Now consider the orbit and rotation state, because geometry is destiny for climate. A close-in planet around a small star is likely tidally locked, with one hemisphere facing permanent day and the other permanent night. The sky becomes asymmetric, and the planet's weather becomes a constant attempt to erase that asymmetry. Tidal locking does not automatically kill habitability, despite how alien it sounds. It creates a circulation problem, and the outcome depends on atmospheric thickness, ocean heat transport, and how efficiently the planet moves energy away from the substellar point. In models, the difference between collapse and stability can be a few bars of pressure, or a few % change in cloud reflectivity. With a thick atmosphere, winds can move heat from day to night and prevent atmospheric collapse, keeping gases from freezing out on the dark side. With a thin atmosphere, the night side can freeze volatiles and create extreme gradients that strain stability. The planet can become a world of two climates, stitched together by a narrow and fragile boundary. The day side can become a cloud factory, and that can be a stabilizing mechanism rather than a sign of chaos. Strong heating drives convection, which can build reflective clouds that cool the surface and stabilize climate depending on particle properties and precipitation efficiency. If droplets grow large and rain out quickly, the shield fails, but if they remain suspended, the shield persists. In visual terms, you might imagine a permanent storm tower under the star, a bright plume that continually reforms as air rises and cools. That plume could act like a shield, reflecting starlight and lowering the temperature below. Around it, winds would stream outward at high altitude, then return near the surface like a planetary-scale sea breeze. The night side can become a cold trap, and cold traps are slow climate thieves. Water can condense and freeze there, slowly draining the atmosphere and drying the day side over long timescales unless winds and oceans return it. The process can be subtle, taking thousands or millions of years, yet it can permanently change the planet's inventory of water. Between them lies the terminator, the twilight ring where temperatures can be moderate and gradients can be gentle. Terminator habitability is a plausible niche, but it depends on winds, clouds, and whether water remains mobile rather than locked away. The terminator can be a corridor of tolerable conditions, or it can be a stormy boundary that never settles. Global circulation can also reshape what transmission spectroscopy sees, because Webb does not measure the whole planet at once. Webb measures the terminator region, not the day side or night side, so the spectrum is a slice of a dynamic boundary. We are sampling air that is constantly moving, mixing day-side chemistry with night-side condensation. If the terminator is cloudy, the spectrum can look flat even if the day side is clear, and that can mislead us about composition. If the terminator is clear, the spectrum can look rich even if the day side is hazy, which can inflate confidence. The planet can present a curated face, and we might mistake that face for the whole. This creates a tension between climate truth and spectral truth, and it is not easily resolved. We can detect molecules in a limb that is not representative of the whole planet, then mistake that limb for the planet itself. The question becomes, are we reading the atmosphere or are we reading the viewing geometry? Now we build the energy budget into a habitability test, because budgets are where intuition meets equations. Incoming power is set by stellar luminosity and orbital distance, while outgoing power is set by temperature and emissivity. In radiative equilibrium, the planet must shed what it absorbs, but the path that energy takes can be long and complicated. Albedo and greenhouse determine which temperature satisfies that balance, and both can shift with time. Change either one and the same orbit yields a different climate, sometimes by a large margin that dwarfs the original headline number. A planet can drift across thresholds without moving an inch, simply by changing its atmospheric makeup. So a 120-degree estimate can be a narrow ridge between outcomes, not a stable plateau. A small increase in greenhouse gases can push the planet toward runaway warming, while a small increase in albedo can pull it back. The ridge is steep because water vapor itself is both a greenhouse gas and a climate response. Runaway greenhouse is the nightmare scenario behind the headline, and it is grounded in basic thermodynamics. If water vapor increases with warming, it can trap more heat, evaporate more water, and accelerate the process until oceans become steam. Once the upper atmosphere becomes wet, ultraviolet light can split water, and hydrogen can escape to space. Yet clouds can counteract that feedback, and this is where models diverge. Reflective clouds can increase albedo as the planet warms, creating a stabilizing loop, though the sign of the feedback depends on microphysics we cannot yet measure directly. The uncertainty is not only about cloud amount, but about droplet size, ice formation, and vertical mixing. The uncertainty is not a flaw of the method, it is the nature of climate, because climate is an emergent property. Even on Earth, clouds are one of the largest uncertainties in predicting future temperature, despite dense observations and decades of modelling. On K2-18b, we are trying to do climate science with a handful of photons and a set of priors. For K2-18b, we must also consider atmospheric escape, because close-in planets can lose hydrogen and water under stellar radiation. The loss rate depends on magnetic fields, upper atmosphere chemistry, and whether the star's early activity stripped the planet when it was most vulnerable. A planet can begin as a mini Neptune and end as a stripped core, and the climate story changes midstream. If K2-18b began with a thick envelope, it might still be shedding it, leaving a transitional atmosphere that changes over geological time. If it began with a thin atmosphere, it might have already lost key volatiles and become dry, even if water vapor appears in trace amounts. Either way, the present-day spectrum may be a snapshot of a long evolution, not a stable endpoint. Water is the central suspect because it links climate, chemistry, and life, and because it has strong spectral features. Water vapor in a spectrum suggests reservoirs, but it does not confirm oceans, and it does not confirm surface liquid. It can also signal a steam atmosphere, where water is abundant yet never condenses into a stable sea. Water vapor can exist above a dry surface, and that possibility matters for interpretation. It can be produced by photochemistry, delivered by impacts, or maintained in a steam atmosphere that never condenses into stable oceans. The question is not only whether water exists, but whether it cycles, condenses, and persists. Liquid water depends on temperature and pressure together, which is why pressure keeps returning like a refrain. At higher pressures, warm water remains liquid, and warm oceans can support robust microbial metabolisms that are not constrained by human comfort. The phase diagram is unforgiving, but it is also generous in the right pressure range. Warm oceans can also be productive if nutrients circulate, because biology is chemistry in motion. Productivity depends on mixing, energy sources, and the availability of elements like phosphorus, iron, and sulfur, which are often delivered through rock interaction. Without circulation, even a warm ocean can become stratified, with life limited to thin layers where nutrients and light overlap. A warm, wet world can be biologically rich without being Earth-like, and Earth itself offers analogues in extremes. Microbial ecosystems can thrive in hot springs, hydrothermal vents, and warm shallow seas if chemistry supplies gradients and stability supplies time. The deeper question is whether K2-8b can sustain those gradients for millions of years, not whether it matches our climate preferences. But a warm world can also be a false paradise, and the spectrum alone may not warn us. If pressure is too high, the surface can be inaccessible, and life might be confined to layers we cannot probe with transmission spectra. If pressure is high enough, even surface becomes a misleading word, replaced by a continuum of increasing density. If pressure is too low, water is transient and the planet is a desert with a warm sky. In that case, the 120-degree number is a distraction from the real limit, which is the inability to keep liquid water stable. The planet could look inviting in temperature headlines, yet be chemically starved and physically dry. So we need to separate habitability from comfort, because comfort is a human intuition about temperature. Habitability is a physical question about stable liquid water, energy flow, and long-term chemistry, and those can align or diverge. A world can be uncomfortable to us, and still be a thriving microbial planet. We also need to separate habitability from evidence of life, because they are different claims with different burdens. A planet can be habitable and sterile, and a planet can be marginal and still host extremophils that exploit narrow refuges. The universe does not owe us a clean correlation between nice climate and living planet. At this point, the claim of 99.7% chance of life feels premature, because climate context multiplies the alternatives. Climate context shows how many non-living worlds can wear a warm mask, especially when clouds and hazes blur the spectrum. The more we learn about sub-Neptunes and ocean worlds, the more we learn how many ways a planet can look promising and still be empty. Yet the same context also keeps the door open, and that is the tension that makes K2-18b compelling. If K2-18b has moderate pressure, persistent water, and stabilizing clouds, a warm climate could support active biology. The planet becomes a test of whether our models can separate a living atmosphere from a merely complicated one. If the terminator is temperate and the atmosphere is thick enough to redistribute heat, a tidally locked world can maintain stable regions for long periods. Stability is not guaranteed, but it is not forbidden either, and that distinction matters. The terminator could be a ribbon of habitability, thin in geography yet long in time. If hazes provide UV shielding while still allowing photosynthetically useful light, surface or near-surface ecosystems become plausible. The star's spectrum sets constraints, but adaptation can exploit niches we would not choose. The question becomes, how much light is enough, and how much radiation is too much for biochemistry to persist? If the planet is water-rich with ongoing mixing and geochemical inputs, microbial productivity could be high and persistent. In that case, atmospheric chemistry could reflect that activity, though interpreting those signals demands caution. Even on Earth, biology's fingerprints are entangled with geology, and that entanglement is the rule, not the exception. But every one of those ifs is a parameter we do not directly measure with a single data set. Webb gives us a spectrum, and the spectrum must be interpreted through models of climate and composition that can fit the same features in different ways. The mystery is not whether the data are real, but which story the data actually support. This is the thin line between paradise and furnace, and it is thinner than the headline implies. The same orbit can host a warm ocean world, a steam greenhouse, or a gas-draped mini-Neptune with no surface at all. The planet's radius, mass, clouds, and chemistry decide which of those worlds is real. The tension is the point, because it forces discipline in how we talk about evidence. A single temperature headline can hide multiple realities, and our job is to keep them separate until the data forces convergence. If we rush, we do not just risk being wrong, we risk training ourselves to accept weak inference as certainty. So we return to the central question with sharper tools and a more cautious imagination. Did Webb glimpse a living world, or did it glimpse a warm atmosphere that only looks promising from far away? And if the answer is we cannot yet tell, what would it take to tell? More wavelengths, repeated transits, or a different kind of measurement entirely? The next step is chemistry that resists equilibrium. Habitability is not life, and biosignatures require molecular patterns that nature struggles to fake. Next, we examine which molecules count as evidence, why combinations matter, and why the universe is skilled at false positives. We have a spectrum and a climate sketch, but life demands a stricter kind of evidence that survives skepticism, survives alternative physics, and survives the slow, patient bias of chemistry. A distant planet can look inviting in broad strokes, with a temperate estimate and a hint of vapour, yet the real test is whether its atmosphere behaves like a system being actively maintained. In practice, that means asking whether the air is drifting towards stillness or being pushed, again and again, away from the quiet end state. The next step is chemistry that should not coexist for long, unless something keeps restoring it, because in nature the easiest state is usually the quiet one. The deeper challenge is that we are not measuring life directly, but the energetic bookkeeping that life would have to pay for. In the visuals, the planet is a small, dark coin against a star, and the spectrum is a thin ribbon of light with shallow notches. Those notches are not photographs of oceans or forests, but they are not nothing either, because they encode how atoms and bonds absorb photons at specific energies. They are the imprint of molecules filtering starlight through a narrow ring of atmosphere at the terminator, where day turns to night in a thin, moving boundary. That geometry matters, because we are not sampling the whole planet evenly, and we are not seeing the surface at all. We are seeing a limb, cold on one side, warm on the other, where winds, clouds, and chemistry meet. In a sense, we are reading a planet through its edge, like judging a city by the haze above its skyline. Scientists use two related terms that sound interchangeable, but they carry different burdens when the stakes include a claim of life. A biosignature is a pattern best explained by biology after alternatives are stressed, modelled, and found wanting under realistic conditions. A bioindicator is a suggestive clue that can raise priors without proving a living source, and it often functions like a signpost rather than a fingerprint. That distinction matters because a signpost can point toward a destination, while a fingerprint implies a specific hand. Historically, this caution grew out of hard lessons in planetary science, where early hopes for canals on Mars or vegetation on Venus dissolved under better data. The history is not merely embarrassing, it is instructive, because it shows how easily human pattern finding outruns the evidence. Bioindicators often describe habitability more than biology, and that difference shapes how cautiously we should speak. Water vapour can imply reservoirs and cycling, yet it can also exist in sterile steam above magma, or in a thin veneer of ice sublimating in sunlight. Carbon dioxide can stabilise climate and feed a carbon cycle, yet it is common in lifeless atmospheres from Mars to Venus where chemistry runs without cells. Even temperature itself can be a bioindicator, because liquid water conditions can exist without any biochemistry ever getting started. A planet can be right in the textbook sense, and still be empty in the biological one. Habitability is a stage direction, not proof that anyone ever walked onto the stage. A biosignature is rarely one molecule, because single molecules have too many abiotic pathways and too many ways to be misread in a spectrum. The strongest claims usually rely on chemical disequilibrium, where oxidants and reductants persist together in the same atmospheric column. That persistence implies continuous replenishment, or physical separation, or an unseen energy source that keeps the mixture from relaxing. In plain terms, disequilibrium is chemistry that looks like it is being held apart. When you see it, you're not just reading composition, you're reading a struggle against time. You're also reading kinetics because reaction rates, not just thermodynamic preference, set how fast the atmosphere can forget what made it. Chemical equilibrium is the quiet end-state chemistry prefers, given time and no forcing, and it is the state toward which reactions drift like a ball rolling downhill. In equilibrium, reactive gases destroy each other, and the atmosphere settles into stable combinations that minimize free energy. For a given temperature and pressure, there is a preferred set of molecules that want to dominate, because they sit in deeper thermodynamic valleys. Disequilibrium means the atmosphere is being pushed away from that end state, like a spring kept compressed by an unseen hand. The deeper idea is thermodynamic. If you see a persistent gradient, you should ask what work is maintaining it. In a planetary context, work can mean sunlight, internal heat, lightning, or the metabolic machinery of life. On Earth, life is a planetary-scale forcing that can maintain disequilibrium for billions of years, and it does so by harvesting energy and exporting entropy. Oxygen remains high because photosynthesis replenishes it faster than sinks remove it, even though oxygen wants to react with rocks and reduced gases. Methane persists because biology emits it continuously, despite rapid oxidation, and despite the atmosphere's tendency to cleanse itself. Earth's air is not merely a mixture, it is a long-running experiment in sustained imbalance. If Earth's biosphere went silent, oxygen would not vanish overnight, but the long arc would bend toward a different, quieter chemistry. Over geological time, even the oceans and crust would slowly reassert themselves as sinks, pulling the atmosphere toward a more reduced, less reactive state. The classic disequilibrium pair is oxygen with methane, because they react on geologically short timescales and should not share the same sky at high levels. In Earth's modern atmosphere, methane's lifetime is roughly a decade, limited by reactions initiated by hydroxyl radicals, while oxygen is constantly replenished by photosynthesis. Another strong pattern is oxygen with nitrous oxide, though detectability is harder at distance because N2O can be faint and blended with other bands. Even without oxygen, mixtures of reduced gases with oxidized carbon can be suspicious in context, especially if the planet's temperature and UV environment predict rapid destruction. The key is not the romance of a molecule, but the lifetime it should have. A short lifetime paired with a high abundance is an implied engine, and engines demand an explanation. But context is everything, because disequilibrium is not a synonym for life, and chemistry has many ways to look busy. A planet can be forced by UV, volcanism, or water, rock chemistry, and still look restless even if it is sterile. The question is not only what molecules exist, but what processes can sustain them at the observed abundances. In practice, that means turning a spectrum into a set of competing stories, then asking which story breaks first. The discipline here is almost narrative, except the plot is constrained by kinetics, radiative transfer, and mass balance. Every proposed source must pay the bill in atoms and energy, and the accounting is unforgiving. For K228b, the headline tension comes from reported features interpreted as water and carbon chemistry, seen as subtle dips and slopes across Webb's infrared bands. Water is the habitability anchor because it links temperature, pressure, and solvent potential in a single, physically meaningful word. Yet water alone is not a biosignature, because it is abundant in many sterile settings, including icy moons and hot, desiccating atmospheres where vapor is only a transient trace. When the narrator says water, the scientist hears a longer sentence. Water under what pressure, at what altitude, and in what circulation regime? In transmission, the water we detect could be high, thin, and cold, more like a misty stratosphere than a sea-level sky. The visuals can linger on that idea, showing a bright crescent of haze at the limb while the surface remains hidden in darkness. Carbon dioxide is often the next anchor, because it shapes greenhouse warming and can indicate carbon reservoirs that exchange with surface or interior. CO2 can also signal photochemical processing of carbon species, depending on UV and mixing, and it can be produced by outgassing without any surface cycle at all. On Earth, CO2 participates in a long geological thermostat through weathering and carbonate formation, but that elegant feedback is not guaranteed elsewhere. In retrievals, CO2 sometimes trades off with clouds and temperature profiles, because both can deepen or flatten the same spectral regions. A CO2 claim is therefore never just a number. It is a statement about which model family the data prefers. It is also a statement about pressure, because CO2 bands behave differently as collisions broaden lines in denser air. Methane is the molecule that tempts the life narrative, because biology makes it easily on Earth, and because it is a classic product of anaerobic metabolisms, methane can also be geological, especially when water interacts with ultramafic rock, and it can be delivered by outgassing or produced in hydrothermal systems. Its spectral bands in the near-infrared can be strong, yet they overlap with other absorbers and can be muted by clouds. The key is whether methane appears with oxidants that should erase it quickly, and whether the implied replenishment rate is plausible. In other words, methane is not a verdict, it is a demand for a budget. That budget includes not only sources but sinks, photolysis, oxidation, and the slow scavenging of methane by atmospheric radicals. Ammonia is even more intriguing because it is chemically fragile in many atmospheres and because it sits at a crossroads of nitrogen chemistry. In the presence of UV, NH3 can be destroyed rapidly unless it is replenished, converted, or shielded by haze and clouds. Its destruction pathways can be fast enough that, without protection, it becomes a short-lived whisper rather than a stable ingredient. That fragility makes ammonia a potential biosignature in some scenarios, and a photochemical puzzle in others, especially for planets around active stars. If ammonia is real, it forces a question about timescales. What keeps it from being erased between one sunrise and the next? The visuals can emphasize fragility, showing ultraviolet light breaking molecular bonds, then cutting to a replenishing plume, as if the planet is constantly refilling a leaky reservoir. Sulfur species complicate the story, because sulfur sits at the boundary of biology and volcanism, and it cycles through many oxidation states. On Earth, sulfur gases can come from microbes, from volcanoes, and from ocean chemistry, and each source leaves different ratios and co-products. Sulfur dioxide, hydrogen sulfide, and sulfur aerosols can each point to different conditions, yet their spectral fingerprints can blend with other absorbers. In exoplanet spectra, sulfur compounds can also be confused with hazes and complex organics, because their bands can overlap, and because aerosols can smear features into broad shapes. Sulfur is therefore both a clue and a camouflage, depending on how cleanly it separates from the rest of the spectrum. When the spectrum looks dirty, sulfur is one reason, because it can hide inside the same wavelength neighborhoods as more familiar molecules. Complex organics can be read as prebiotic chemistry, or as biological byproducts, or as haze formation driven by sunlight and methane. In transmission spectra, organics often appear as broad features and slopes, not clean isolated lines, because many molecules absorb in overlapping forests of lines. That makes them easy to overinterpret and easy to misattribute, especially when the data are sparse at key wavelengths. The visual impression can be seductive, a gentle tilt in the spectrum that looks like something organic, even when it could be dust-like aerosols. The question becomes whether the slope is a chemical signature, or simply the optical texture of particles floating high above everything else. When we say organic, we should remember the plain language meaning too. Carbon-based chemistry is common, and life does not own it. So we need to separate what the data detects from what the story claims it means. Detection is about whether a feature is present beyond noise and systematics, and whether it repeats under different assumptions. Interpretation is about whether that feature uniquely points to biology, which is a much higher bar than simply consistent with. The difference is philosophical as much as technical, because one is measurement and the other is inference. A spectrum can be honest and still be ambiguous, because the same shadow can be cast by different objects. The documentary's suspense lives in that gap, where a clean-looking dip can carry multiple, incompatible explanations. The hard problem is that spectra are underdetermined, because different atmospheres can look similar when filtered through limited resolution and limited wavelength coverage. Multiple mixtures can produce overlapping absorption bands at Webb's resolution and wavelength range, especially when clouds flatten contrast. Retrieval models can return confident posteriors even when the parameter space is degenerate, because the math can be certain about the wrong family of explanations. This is not a flaw of Webb, it is the reality of inferring a three-dimensional atmosphere from a one-dimensional shadow. The instrument measures wavelength-dependent transit depth, and we must translate that into composition, temperature, and clouds, an inversion that is never unique. In the visuals, the spectrum becomes a single silhouette, while the possible atmospheres multiply behind it like branching corridors. Degeneracy begins with clouds and hazes, because aerosols can mute or reshape molecular bands, and because their particle sizes set how opacity changes with wavelength. A high cloud deck can make a rich atmosphere look empty, or push retrievals toward incorrect abundances by hiding deeper layers. Haze can add smooth opacity that mimics organics, or hides them, and it can also shift the apparent continuum that all molecular features sit on. The physics is simple in principle. Small particles scatter more strongly at shorter wavelengths, while larger particles flatten the spectrum. Visually, the spectrum becomes a landscape seen through fog, where the hills are real but their heights are uncertain. Even the altitude of the cloud tops matters, because transmission only probes down to where the atmosphere becomes opaque along the slant path. Degeneracy also comes from temperature structure, because line strengths depend on temperature and pressure, and because the limb is not a single temperature. A warmer limb increases scale height and deepens features, which can mimic higher abundances even if composition is unchanged. A cooler limb can flatten features, which can mimic clouds, especially if the terminator has strong day-night contrasts. On some planets, the terminator may sample both a hot day-side flow and a cold night-side return, braided together by winds. The atmosphere is not a static shell. It is a moving boundary where winds and radiation reshape the very conditions we try to retrieve. In a visual sequence, the terminator can be shown as a band of shifting cloud, sliding around the planet like a slow tide of air. Even the star can create degeneracy, because stellar heterogeneity changes the baseline spectrum that the planet is measured against. Spots and faculae can imprint wavelength-dependent slopes that resemble atmospheric absorption, and they can change over time as the star rotates. If stellar contamination is not modelled, retrievals can invent molecules to compensate, fitting a stellar artifact with a planetary gas. This problem is especially sharp for small, cool stars where magnetic activity can be stronger and surface features can cover larger fractions. The planet's shadow is therefore never pure. It is projected onto a star that has its own weather. Historically, the field learned this lesson as transit spectroscopy matured, because early analyses often treated stars as uniform light bulbs, an assumption that nature refuses to honour. Against that backdrop, the documentary's tension is a claim of disequilibrium leaning toward life, framed as chemistry that looks too unstable to be accidental. The life-leaning interpretation says the atmosphere contains a mix that should react away quickly, given known kinetics and UV flux. If it persists, a replenishing source is implied, and biology is one candidate among several. The mystery is not that the spectrum has features, but that the implied chemistry seems unwilling to settle. That unwillingness is the hook, an atmosphere that behaves less like a closed bottle and more like an open system. The question becomes almost intimate. What is the planet doing hour after hour to keep its air from relaxing into silence? The dangerous counterpoint is that nature has many abiotic replenishment engines, and several of them are common wherever there is heat and water. Hydrothermal systems can generate methane through serpentinization, where water alters rock and releases hydrogen as minerals reorganize. Hydrogen can then reduce carbon to methane without any biology, and the reaction can proceed in porous crust for long periods. In the mind's eye, this is not a green world. It is a dark seafloor, warm fractures, and slow chemistry in the absence of light. The energy source is not sunlight, but the planet's interior, leaking heat into water like a long, steady breath. On Earth, related environments exist at mid-ocean ridges, where chemistry can run for ages without ever needing a photon. Serpentinization is not a loophole. It is a known planetary process that can run long, and it has been studied in Earth's oceanic crust for decades. It depends on liquid water, heat, and certain rock types, which are plausible on many worlds with differentiated interiors. It can produce methane steadily, and it can also produce chemical gradients that life could exploit, which complicates interpretation even further. The same gradients that mimic biology can also provide the scaffolding biology needs, which makes abiotic and biotic less like opposites and more like neighbours. When geology can both imitate life and feed life, the spectrum becomes a riddle with layered answers. The unsettling thought is that a planet can look alive precisely because it is chemically fertile, even before any organism appears. Volcanism is another engine because it can inject reduced gases and aerosols episodically, and because it can reset atmospheric chemistry on short timescales. Outgassing can deliver methane, sulfur species, carbon monoxide, and hydrogen, depending on mantle chemistry and oxidation state. A volcanic planet can look chemically active, even if it is sterile, and its spectrum can change as plumes rise and decay. The visuals here are dramatic. Towering columns, ash-like aerosols, and an atmosphere briefly thick with reactive gases. Yet the science is equally stark, because a single eruption can overwhelm slow background processes and dominate what we infer from a few transits. The planet we observe may be caught in a transient mood, and we might mistake that mood for its personality. Impacts can also reset atmospheres, delivering volatiles and creating transient chemistry, and the early histories of many planets are written in craters. After a large impact, shock chemistry can produce unusual mixtures and hazes, and it can loft dust that alters radiative balance. Those signatures can persist for a while, then fade, which can mimic variability if observations catch the planet at an unusual moment. In the solar system, the scars of bombardment are a reminder that stable is often a late chapter, not an opening one. A single collision can create a spectral personality that lasts longer than a human career. When we look at an exoplanet, we rarely know whether we are seeing a mature equilibrium or the long afterglow of violence. Photochemistry can generate false positives that are tailored to the star's UV spectrum, and that dependence makes M-dwarf systems especially tricky. Under certain UV regimes, methane can be produced or preserved longer than expected, because key destruction pathways are suppressed. Under other regimes, methane and ammonia are destroyed quickly, pushing chemistry toward oxidized products and thick hazes. Photochemical networks are not one reaction but thousands, linked by radicals that appear and vanish in fractions of a second. The same molecule can therefore mean different things under different suns, which is why stellar characterization is not a side quest. In visuals, this can be rendered as a web of reactions, lighting up and dimming as ultraviolet intensity changes. Stellar-driven chemistry can also create oxygen without life, which is a classic trap that has been discussed since the earliest biosignature debates. If water is split by UV and hydrogen escapes to space, oxygen can accumulate, especially if surface sinks are limited. That oxygen can then look like a biosignature, even though it is a byproduct of loss, a ghost left behind by escaping hydrogen. On a dry world with little volcanic outgassing, oxygen can linger because there is less reduced material to consume it. The haunting question is whether an oxygen-rich atmosphere is a sign of thriving photosynthesis, or a sign of a planet slowly drying out. In a wide shot, the planet's limb can glow faintly, beautiful and misleading, as if the air itself is telling a story it did not earn. Atmospheric escape is especially relevant for close-in planets around active stars, where high-energy radiation can heat upper layers and drive hydrodynamic outflow. Escape can remove hydrogen and leave behind heavier species, changing mean molecular weight and scale height, which then feeds back into how deep spectral features appear. It can also change redox balance, creating oxidized atmospheres that look biologically processed even when they are not. In the visuals, escape is suggested by a faint comet-like tail, but in the data it is more subtle, an altered baseline that shifts every inference downstream. In the spectrum, escape is invisible directly, yet its fingerprints can be written into everything else. Even the absence of expected light gases can be a clue, because absence can be as diagnostic as presence when you know what should survive. Haze chemistry is another trap, because hazes can mimic the spectral fingerprints of complex organics, and because they can dominate transmission spectra by blocking deeper layers. Photochemical hazes can form from methane and nitrogen chemistry, even without biology, producing tholins and other complex polymers. Those particles can loft high, where they intercept starlight before it reaches the denser, more informative layers below. In spectra, hazes can create broad absorption and slopes that invite narrative leaps, especially when the data are noisy at the edges. The planet becomes a silhouette behind a veil, and the veil itself can be mistaken for a signal. Visually, the haze can be shown as a luminous ring, beautiful in backlight, while the true atmosphere remains hidden beneath. So the question becomes a structured elimination problem, not a single dramatic detection. If we see methane, we ask whether serpentinization can supply it at the required rate, given plausible crustal composition and heat flow. That rate matters because an observed abundance implies a steady flux when lifetimes are short, and fluxes can be compared against realistic geological power. If we see sulfur, we ask whether volcanism can explain both abundance and variability, and whether the implied eruption frequency is realistic. Each inference becomes a calculation, because every molecule implies a source strength and a sink strength. In the visuals, numbers can appear briefly beside arrows, turning the mystery into a ledger that must balance. If we see ammonia, we ask how it survives UV and whether shielding or replenishment is required, and whether photochemical models can keep it aloft at the limb. If we see oxygen or an oxidant proxy, we ask whether escape could have produced it, and whether surface reactions would remove it quickly. Each molecule is a clue, but each clue has a list of non-living suspects, and the suspects are not exotic. The method is almost forensic. Reconstruct the scene, test the alibis, and see which story remains standing. What makes it difficult is that the scene is a planet we cannot visit, and the evidence is a few parts per million change in starlight. That is the scale of the challenge, building a world model from a whisper. Now we revisit the pulsing clue because time variability can strengthen or weaken a biosignature claim, depending on what exactly changes. If features change between epochs, it could reflect seasons, storms, or shifting cloud decks, and those are atmospheric processes we already expect. It could also reflect episodic outgassing or changing stellar contamination, which can masquerade as planetary change. Variability is therefore a double-edged signal, exciting yet easy to misread. The same pulse can be a heartbeat, or it can be an instrument breathing, or a star turning its spotted face toward us. The visual language can echo that ambiguity, cutting between a rhythmic waveform and a rotating star whose surface patterns drift like weather. Seasonal biology is one explanation, but it is not the default explanation, and it is especially complicated on worlds unlike Earth. On a tidally locked world, variability could be dominated by circulation shifts and cloud migration, with a permanent day side feeding a permanent night side. A changing terminator cloud deck can alter apparent molecular depths without changing global composition, because transmission spectra sample a thin ring of atmosphere. The terminator is a moving boundary, and our measurement is a narrow slice through it. Even on Earth, the strongest biological seasonality is regional, and a limb average spectrum would smear those signals into something subtle. The question to sit with is simple. If life is there, would we even see its seasons from this far away? Instrument and pipeline differences can also create apparent variability, which is why repeatability matters and why careful teams obsess over calibration. If different visits use different modes, the systematics can differ in wavelength-dependent ways, creating false changes where none exist. A robust pulsing claim must survive identical setups and independent reductions, and it must survive scrutiny from people who want it to fail. In practice, the most valuable variability is the kind that repeats with orbital geometry, not the kind that appears once and vanishes. The discipline is to treat each new epoch as a test, not a confirmation. In the visuals, repeated transits can stack like pages, and the audience can watch whether the same features return in the same places. This is where the 99.7% number becomes a trap, because it compresses uncertainty into one headline, and headlines are not models. It might reflect confidence that a spectral feature exists in the data, meaning the dip is not random noise under a particular statistical test. It does not automatically reflect confidence that the feature is biological, or even that the molecule identification is unique. A number can be precise while the interpretation remains broad. The danger is that precision feels like truth, even when it is only conditional truth. The question to ask is always, 99.7% of what, under which assumptions, and compared to which alternatives? A 3 sigma style detection can be real and still be misidentified, because significance is not the same as correctness. A posterior probability can be high within a narrow model family, and still ignore plausible alternatives that were never included in the comparison. In retrieval work, the choice of priors, the treatment of clouds, and the assumed temperature profile can each tilt the outcome, sometimes subtly and sometimes decisively. The number is only as meaningful as the question it answers, and the question is often narrower than the public assumes. When the public hears 99.7, it hears certainty, yet the scientist hears conditional confidence. Historically, astronomy has lived through similar moments, where impressive sigma values later softened as systematics were understood, and models became more realistic. Scientists stress test claims by expanding the question, then watching confidence change as more realistic assumptions are allowed. They compare alternative atmospheric models and compute Bayesian evidence for each, asking which model earns its complexity rather than merely fitting noise. They test whether adding a molecule truly improves fit, or merely absorbs systematics that should have been modeled differently. Retrieval is not just curve fitting, it is model comparison under uncertainty, and the penalty for complexity is part of the logic. The goal is not to win an argument. It is to find the simplest explanation that survives contact with the data. In the visuals, competing models can be shown as translucent layers, each fitting the spectrum but implying a different planet. They run independent pipelines to reduce the same raw data, looking for convergence that suggests the signal is not a software artifact. They check cross-instrument consistency, because different detectors fail in different ways, and because independent channels provide independent constraints. They repeat observations across epochs, because real atmospheres repeat patterns tied to orbital geometry, while many systematics do not. Over time, the evidence becomes less about one beautiful spectrum and more about a pattern that refuses to go away. In the visuals, the spectra stack like transparent sheets, and the question is whether the same notches align. The audience can almost feel the patience involved, because each new transit is a small addition to a slow, cumulative argument. They also test for stellar contamination explicitly, using spot and facular models and out-of-transit monitoring that tracks how the star's surface changes. They examine residuals for correlated noise, because correlation inflates false certainty and can create phantom features. They publish priors and sensitivity tests because hidden assumptions are where weak claims hide, and because transparency is a defense against self-deception. The culture of exoplanet spectroscopy has learned these lessons the hard way, through early overclaims and later corrections. In that history, humility is not a personality trait, it is a method. The method is what turns wonder into knowledge, even when the answer is disappointing. Even after all that, a living interpretation remains a hypothesis, not a verdict, and the documentary's mystery remains intact. The best case is a robust set of features that resist abiotic explanation under realistic stellar and planetary conditions, even when skeptics try to break them. The worst case is a chemically plausible mirage built from degeneracy and incomplete context, a story that fits because the model was too small. Between those extremes is the honest middle, where the data are suggestive and the uncertainty is real. The question is not whether we want life, but whether the evidence can carry that weight. And if it cannot, yet, what would it take for the balance to tip? So the chapter ends on the documentary's dilemma, sharpened rather than resolved, because the most interesting questions are often the ones that survive the first wave of answers. If the signal is robust, what else could it be besides life, given the planet's temperature, UV environment, and plausible geology? And if it is not life, what does that teach us about how planets imitate biology, and about how easily our expectations can be tricked? The unsettling possibility is that the universe can produce convincing masks. If so, the masks are not a disappointment, they are a discovery about planetary chemistry itself. A planet that can counterfeit life is still telling us something profound about the range of nature's experiments. The next step pulls back from one world to the population question, because context can come from statistics, and statistics can turn anecdotes into evidence. How common should such atmospheres be, given planet formation and stellar environments, and given the diversity already seen in smaller samples? If K2 and 18b is truly special, the galaxy should tell us so, not in a single dramatic announcement, but in a slow accumulation of comparable cases. A lone outlier can be a discovery, yet a pattern across many worlds becomes a framework. The census approach is slow, but it's how astronomy turns whispers into knowledge. In visuals, the single planet can recede into a field of dots, each one a potential atmosphere waiting to be read. We move from a single spectrum to a cosmic census, because rarity and frequency are part of interpretation, and because biosignatures are stronger when they are not easy to reproduce by chance. If many worlds show similar disequilibrium without life, biosignatures become less decisive, and the bar for proof rises accordingly. If such patterns are rare, the life hypothesis gains weight, but only after the same rigor holds, and only after the same traps are ruled out again and again. In the end, the chemistry that should not coexist is not just a clue about life. It is a test of how carefully we can read a faint shadow against a distant star, and it is a reminder that the universe may be subtle, offering hints that demand patience rather than applause. K2 for 18b begins as a spectrum and a probability, but it ends as a census problem, because one persuasive atmosphere forces us to count differently. If that air truly carries biology, one world rewrites the baseline for every other world we have not yet read. The discovery would not just add a data point, It would bend the curve of expectation across the galaxy. It would also change how we design surveys, because the first confirmed case becomes the template for the next search. In the mind's eye, the planet is still a thin silhouette crossing its star, a black coin sliding over a glowing disk. The star's light looks steady until the moment it doesn't, when the brightness dips by a fraction that only careful instruments can track. We are not seeing continents or storms directly, only a slight dimming, repeated with clockwork regularity across many orbits. Yet inside that dimming is a measurement of scale, and inside the scale is a story about density, temperature, and chemistry. The transit is geometry turned into evidence, an alignment that converts a distant system into a measurable experiment. The depth of the dip tells us the planet's radius relative to the star, and the duration hints at orbital speed. The timing, repeated again and again, gives the period with exquisite precision, like a metronome embedded in starlight. When the data are clean, even small deviations can suggest additional planets tugging on the orbit. A shadow can carry a surprising amount of information if you know how to read it. We pull back from the Terminator and ask what the galaxy has been building all along. Planets are not rare accidents now because Kepler turned the sky into a demographic survey. It stared at one patch of stars for years, watching for tiny periodic dips in brightness that would have been dismissed as noise a generation earlier. That patience mattered, because transits are brief, and the signals are small, and the universe does not advertise its worlds. Kepler's legacy is not a catalogue, it is a rate, an estimate of how often nature repeats itself when you look long enough. The mission did not just find planets, it measured occurrence, the statistical heartbeat of planetary formation. Around many stars, planets with radii between Earth and Neptune appear in abundance, filling the size range our own system barely samples. The surprise was not a single Earth analogue, but the sheer number of near misses. Worlds that are a little bigger, a little warmer, a little more shrouded than we hoped, yet still close enough to tempt our definitions. Kepler also taught us what common means in a universe that hides most of its planets. The transit method only works when geometry cooperates, when an orbit happens to line up with our line of sight to the star. For every transiting planet, many more exist unseen, their shadows missing Earth by a fraction of a degree. So the raw count becomes a corrected population, and the corrected population becomes a new intuition about how crowded the galaxy really is. That correction is not hand-waving, it is baked into the math of probability. The chance of a transit scales with the star's radius divided by the orbital distance, so close-in planets are favoured even if they are intrinsically rare. Detection also depends on noise, stellar variability, and the number of observed transits, which means long-period temperate worlds are harder to confirm. Kepler's long stare helped, but it still had limits, and those limits shape what typical looks like. Our first demographic portrait is therefore accurate in broad strokes, but incomplete in the quiet corners. In that population, the habitable zone becomes a statistical band, not a promise, an annulus where starlight could allow liquid water under some atmosphere. It is a radiative concept first, defined by energy balance, and then complicated by clouds, greenhouse gases, and planetary albedo. For sun-like stars, Earth size in the habitable zone is not absurdly rare, though the uncertainties remain stubborn. For M-dwarfs, the habitable zone is close in, and detections multiply. The orbits are short, the transits are frequent, and the signals are easier to stack until faint patterns become visible. This matters for K2-18b because it orbits a small star, and small stars dominate the galaxy. M-dwarfs are the Milky Way's quiet majority, dim and long-lived, burning their fuel slowly over timescales that dwarf the Sun's future. They are also small in radius, which makes a planet's transit deeper and easier to measure. If life can persist around them, the universe has many more chances. If they sterilize their planets early, the universe has fewer, and the cosmic inventory of living worlds shrinks. That early phase is not a footnote, because young M-dwarfs can be violent. They flare in ultraviolet and X-rays, and they can drive powerful stellar winds that buffet close-in planets. Those energies can erode atmospheres, split molecules, and push planets toward runaway chemistry that locks water away or strips it entirely. In the most extreme cases, a planet can lose an ocean's worth of hydrogen to space, leaving behind oxygen that looks biological but is not. So a living K2-18b would be a clue about survival, not just about origin. Kepler also revealed another lesson, hidden in the radius distribution like a geological fault line. There is a radius valley that hints at atmospheric loss and divergent histories, a gap between small rocky worlds and slightly larger sub-Neptunes. Some worlds keep thick envelopes and some get stripped to denser cores, and the population splits as if nature prefers two outcomes. The valley suggests that small differences in mass, irradiation and formation time can produce very different planets. It also warns us that radius alone can mislead, because two planets of similar size can have very different compositions. The physics behind that valley is concrete, even if the details are still debated. High-energy radiation can heat up our atmospheres until gas escapes to space, a process called photoevaporation, where the atmosphere becomes a slow wind. A planet's gravity fights back, and so does time, because stars calm down as they age and their high-energy output declines. Another mechanism, core-powered mass loss, draws on internal heat leaking from the planet itself, inflating the atmosphere until it can spill away. Either way, the result is a split. Puffy sub-Neptunes on one side, compact super-Earths on the other, with few survivors in between. K2-18b sits near that ambiguity, and the ambiguity is cosmological as much as planetary. If it is an ocean world with a thick atmosphere, it is part of a vast class that Kepler hinted at but could not characterize. If it is a rare transitional case, it is a warning about selection effects and interpretive overreach. It might be the kind of planet that is easiest to detect, not the kind that is most common. And if its atmosphere is truly unusual, that unusualness becomes part of the statistical story. When we say sensors, we also mean the biases of the counting process. Transiting planets are overrepresented around small stars, because the relative dip in starlight is larger and the geometry is more favourable. Planets with extended atmospheres are also easier to characterise, because they imprint deeper spectral features on the starlight that skims their edges. So the first worlds we can read may not be the most Earth-like, only the most legible. The universe may be full of subtle biospheres that do not announce themselves in our current methods. Now we widen further, because planets require ingredients that the early universe did not have. The first stars formed from hydrogen and helium, with almost no heavy elements, and that chemical simplicity matters. Without metals, there are no silicate rocks, no complex atmospheres, and no rich biochemistry with catalytic diversity. The early cosmos could shine, but it could not yet build the familiar scaffolding of planets, and it could not easily build the chemical gradients life exploits. In visual terms, imagine the universe after the first few 100 million years, vast dark gaps, and then islands of light. The first stars, likely massive and short-lived, burned hot and died young, their radiation carving bubbles in the surrounding gas. Their deaths were not merely endings, but manufacturing events, cosmic foundries that changed what matter could become. Supernovae and stellar winds seeded the surrounding gas with new elements, and those elements mixed outward like ink in water. The darkness between galaxies began to carry a richer recipe. Cosmic chemical evolution is the slow manufacturing of possibility, an assembly line that runs on fusion and catastrophe. Stars fuse light elements, then die, and seed the interstellar medium with carbon, oxygen, nitrogen, silicon, phosphorus, and iron, each with its own origin story. Some elements are forged in the quiet burning of stellar cores, while others require explosive environments and rapid neutron capture. Every generation enriches the next, raising the ceiling for complexity. The periodic table becomes a timeline, and the timeline becomes a map of potential habitats. Historically, this idea took shape as astronomers learned to read starlight as chemistry. Spectroscopy turned stars into laboratories, revealing absorption lines like barcodes that identify specific atoms and molecules. In the 19th century, those lines began to connect Earth chemistry to the heavens, dissolving the old boundary between terrestrial and celestial matter. When we realized that the Sun is rich in metals, and that older stars are often metal poor, the galaxy became a record of enrichment. The Milky Way was not static. It was evolving in composition, and therefore in what it could build. Life is tied to cosmology because life is chemistry with a supply chain. Carbon and oxygen set the backbone of organics and water, and their relative abundance shapes what molecules are easy to assemble. Nitrogen helps build proteins and nucleic acids, and it can buffer atmospheres by providing an inert background gas. Phosphorus and trace metals enable energy transfer and catalysis, turning raw chemistry into metabolism. Even iron, which seems mundane, becomes a key player in enzymes and electron transport, where tiny shifts in electrons power living systems. In plain language, biology needs parts, and those parts are forged in stars. The question is not only whether planets exist, but whether the right mix of elements arrives in the right places and stays accessible. A world can have water but lack accessible phosphorus, or have carbon but lose nitrogen to space during early atmospheric escape. It can have the right ingredients locked in minerals that never interact with oceans or air. Habitability is therefore not a single switch, but a network of constraints that can fail in many quiet ways. The galaxy's habitability is therefore time-dependent, not just location-dependent. Early epochs may have lacked enough metals for rocky planets in large numbers, so the first chances for life may have been sparse. Later epochs may have enough metals, but also more hazards and more crowded environments, where close stellar encounters and radiation fields are stronger. The same enrichment that enables planets also increases the number of energetic events that can disrupt them. The galaxy becomes a moving target, not a static stage. Heavy elements also change planet formation pathways, because solids are the seeds of everything else. In protoplanetary disks, dust grains stick, grow and settle into a midplane, where collisions can build larger aggregates. Those grains become pebbles, then planetesimals, then cores that can accrete gas if they grow fast enough. The disk is a rotating, turbulent environment where temperature and pressure sculpt what materials can condense and where they can survive. Even the disk's magnetic fields can influence how gas flows and where solids concentrate. The snow line becomes a key boundary in that disk, because water ice can exist beyond it. Ice increases the amount of solid material available, making it easier to build large cores quickly, and it changes how sticky grains are during collisions. That is one reason giant planets are thought to form beyond the snow line, where the building blocks are abundant and growth can outrun disk dispersal. But those cores do not always stay put, and the disk does not keep its boundaries fixed. As the star brightens and the disk evolves, the snow line can move, reshaping where water-rich material forms. Disk physics creates diversity without asking permission from our categories, because the same ingredients can assemble into many architectures. A core can form fast and grab hydrogen, becoming a sub-Neptune with a deep envelope that dominates its radius. A core can form slower or lose gas, becoming a super-Earth with a thinner atmosphere and a more accessible surface. Small differences in timing can decide whether a planet ends up with a thin skin of air or a deep crushing envelope. In a young system, minutes of orbital dynamics can translate into billions of years of climate. Migration is part of that story, not an exception. Planets exchange angular momentum with the disk and drift inward or outward, sometimes smoothly and sometimes in jumps when resonances lock them together. Many worlds do not form where we find them, and their climates inherit that history like a genetic record. A planet that formed in the cold outer disk can carry volatiles inward, arriving as a water-rich body in a warmer zone. A planet that formed closer in can be pushed outward, changing its irradiation and atmospheric evolution. The visual is almost unsettling. Young planets embedded in a glowing disk, carving gaps like wakes in a river. Spiral density waves carry momentum, and the planet's orbit shifts as the disk evolves, as if the system is breathing. Dust lanes brighten and darken, and the star's light scatters through the disk like fog in a headlight beam. The final system is a snapshot taken after a long dance, when the gas clears and the orbits freeze into place. What looks stable now may have been mobile and chaotic early on. With collisions and rearrangements we can only infer. Volatile delivery is another branch point, and it shapes whether a planet becomes dry, wet, or ocean-dominated. Water and carbon compounds can arrive via icy pebbles, planetesimals, and late impacts, and the delivery can be gradual rather than dramatic. The timing of delivery can decide whether volatiles stay or escape, because early stellar radiation can be a thief. If water arrives while the star is still blasting high-energy radiation, the planet may lose much of it through hydrodynamic escape. If it arrives later, it may persist and accumulate into deep oceans. Even on Earth, the origin of water is a continuing debate, woven from isotopes and impact histories. Some water may have been inherited from the disk, trapped in minerals that carried it through accretion. Some may have been delivered later by bodies from farther out, carrying different chemical fingerprints in deuterium ratios and noble gases. That uncertainty is not a weakness. It is a reminder that wet is a pathway, not a default. If we cannot fully reconstruct our own story, we should be cautious about assuming anyone else's. Ocean worlds and thick atmospheres can arise naturally in these pathways, and they may be common among planets slightly larger than Earth. A planet can accrete large water fractions beyond the snowline, then migrate inward before the disk disperses. A planet can keep a hydrogen envelope that inflates its radius and hides its surface from our view. In such cases, the boundary between ocean and sky may be deep, and the surface may be inaccessible to starlight. The world could be habitable in principle, yet difficult for us to interpret from afar. That is why K218b's possible biosignature cannot be separated from formation. If it is water-rich with high-pressure ice, nutrient cycling may be constrained, and the ocean could be chemically isolated. If it is a stripped core with secondary gases, surface exchange may be stronger, and the atmosphere may reflect active geology. The same spectral feature could imply very different geochemical engines beneath the clouds. Our interpretation depends on which history we think the planet lived through. High-pressure ice is not science fiction, it is a phase diagram. Under enough pressure, water forms crystalline structures that are stable even at relatively warm temperatures, and those phases can appear deep beneath an ocean. On an ocean world, that could create an ice mantle between the ocean and the rocky interior, sealing off the seafloor. If that barrier is thick, it may limit the flow of minerals that life could use, and it may reduce the availability of redox gradients. A planet can be wet and still be starved of the chemical contrasts that power metabolism. Yet nature often finds loopholes, and the loopholes become the interesting questions. Could hydrothermal activity punch through in localized plumes, or could convection transport nutrients anyway through fractures and phase transitions? Could life rely on atmospheric chemistry instead of seafloor chemistry, using sunlight or photochemical products as energy sources? Could a biosphere exist in layers, with different metabolisms stacked like ecological floors in a deep ocean? When we say habitable, we're really asking how many energy gradients remain available for metabolism. We return to the central question, because cosmology does not reduce uncertainty, it redistributes it. Did Webb detect a living world, or a planet that only looks alive in a narrow spectral window? The answer changes how we interpret the entire exoplanet census, because it changes what we treat as plausible. It changes whether we treat ambiguous spectra as likely biology or likely geology. It also changes how we prioritize time on the most expensive telescope we have ever built. The measurement itself is subtle, and the subtlety shapes the debate. Transmission spectroscopy samples starlight filtered through a planet's limb, a thin annulus of atmosphere at the terminator where day meets night. The signal is a tiny difference between in-transit and out-of-transit spectra, and it must be extracted from noise with careful calibration. Clouds and hazes can mute features, and stellar spots can imprint false patterns if the star's surface is not uniform. Even the instrument's systematics can mimic or erase weak signals when the data are pushed to the limit. The result is not a photograph, but a statistical inference that must survive every alternative explanation. A single confirmed biosphere would be a new data point with outsized leverage. It would not prove that life is everywhere, but it would push the prior upward, because a second example breaks the loneliness of one. It would force us to update the fraction of habitable worlds that actually become living, even if we remain ignorant about the details. In Bayesian terms, one strong likelihood term can move a distribution that was previously dominated by ignorance. The math is cold, but the implication is intimate because it changes what we think the universe tends to do. Here the Drake equation becomes a narrative tool rather than a prediction machine. It breaks the problem into factors that can be revised as evidence arrives, and it keeps us honest about what we know versus what we assume. Each factor is a door that can swing open or shut, and the hallway behind them is long. The equation is often criticized as speculative, but its structure is useful because it tells us where the uncertainty lives. It also reminds us that rare can hide in many different places. Kepler and radial velocity surveys already constrain the first door. The number of planets is large, and the number of potentially temperate small planets is not negligible, even if their true surface conditions remain unknown. Radial velocity adds mass estimates and reveals planets that do not transit, measuring a star's wobble as planets tug it back and forth. Together, these methods turn maybe into a measured occurrence rate, even if the error bars remain wide and the sample remains biased. The demographic foundation is now solid enough that the debate has moved on. The uncertainty moves to biology and longevity, and that is where one planet can matter too much. If K2-18b is truly alive, the fraction of life-bearing worlds, FL, cannot be extremely tiny, at least for some class of planets. One nearby biosphere would imply that life emerges readily under some common conditions, or that it persists long enough to be caught. Even with selection bias, the posterior shifts, because the universe would have revealed life in our first serious atmospheric readings. That would be a revealing kind of luck. But the size of that shift depends on how we found it, and how many chances we had to find it. If K2-18b was targeted because it was already unusual, the inference weakens because we are not sampling randomly. If it was found in a broad, unbiased survey, the inference strengthens because the detection would be harder to dismiss as cherry-picked. The logic is simple. A lottery win means more if you bought one ticket than if you bought 1,000,000. Our confidence depends on whether the universe volunteered the answer, or whether we hunted until we found something that looked like one. This is where observational strategy becomes part of philosophy. We choose targets that are bright, nearby, and favourable for transit spectroscopy, because we must, given limited telescope time. We prefer small stars because the signals are larger, and we prefer short periods because the transits repeat and can be averaged down. Those choices are rational, but they also sculpt our sample into something that is not the galaxy at large. The first atmospheres we can read are a special subset, and the subset can distort our intuition. Anthropic caution must sit inside every update, even when the data feel thrilling. We exist on a life-bearing planet, so our perspective is conditioned on success, and that conditioning can seep into our expectations. We're not sampling the universe at random, and neither are our telescopes, which are built by a species that evolved under one particular sky. The danger is not that we learn nothing, but that we learn too quickly from too little. A single world can become a mirror for our hopes, and mirrors are not measurements. Even so, one confirmed biosphere would change the statistics of silence. The great filter question would sharpen, not soften, because it would relocate the improbability. If simple life is common, then the bottleneck may be later, somewhere between microbes and machines. The universe would look less like a barren desert, and more like a landscape where something repeatedly starts, but rarely finishes. That is a more unsettling kind of abundance. The great filter is not a single wall, it is a sequence of improbable steps. It could be a biogenesis, the jump from chemistry to replication, where information begins to copy itself with variation. It could be the rise of complex cells, multicellularity, intelligence, or stable technology that survives its own power. Each step has its own timescale, its own vulnerabilities, and its own dependence on planetary context. A filter can also be environmental, because a planet can reset itself with impacts, volcanism, or climate collapse. On Earth, the timeline is suggestive, and it is also humbling. Life appears early in the geological record, but complex multicellular life arrives much later, after long stretches of microbial dominance. The rise of oxygen takes time, and it may require feedbacks between biology and geology, including burial of organic carbon and the oxidation of crustal minerals. Intelligence, at least in our case, is very late, an end cap on a long chain that could have ended differently. It invites a question that is hard to avoid. Was our path typical, or merely survivable? K2-18b would move probability mass away from the earliest filter. It would suggest that chemistry can cross into biology more than once, at least under some recurring conditions. It would make later steps look more suspiciously rare, because the sky would contain life yet still appear technologically quiet. That suspicion would not be proof, but it would be a new pressure on our assumptions. It would also force us to ask what later even means on planets with different oceans, atmospheres, and day lengths. That pressure feeds directly into the Fermi paradox. If life is common, why is the sky silent? If intelligence is common, why is the galaxy not visibly engineered, at least not in ways we can recognize? The paradox is not a single question, but a tension between timescales, distances, and expectations. It is the discomfort of a universe that seems fertile, yet offers no clear reply. One answer is that we are not looking well enough, and our instruments are young. Radio searches cover limited time, limited frequencies, and limited sky, and they often revisit targets only briefly. We have scanned the ocean by dipping a cup, then argued about what the ocean contains, as if absence in the cup means absence everywhere. Technosignatures may be brief, directional, or unlike our assumptions, and they may not repeat on human schedules. The sky could be speaking in a dialect we have not learned. Even our definition of signal is shaped by our own technology. We look for narrowband radio because it is easy to generate and easy to detect against natural backgrounds, and because it matches our own early leakage. Another civilization might use optical lasers, or spread spectrum techniques, or communications that ride on infrastructure we cannot see. They might communicate locally, not broadcast across the galaxy, because broadcasting is expensive and risky. They might also encrypt, compress, or hide in noise, making their presence indistinguishable from natural processes. The silence could be camouflage or simply indifference. Another answer is that the absence is real and it implies constraints. Civilizations may self-limit, self-destruct, or choose quiet, and the reasons could be technological or biological. They may be rare because the path from microbes to machines is steep, requiring stable climates and long uninterrupted time. Or they may be common but short-lived, flickering on timescales that rarely overlap, like fireflies out of sync. If that is true, then the galaxy can be full of life and still feel empty. K2-18b would not solve that paradox, it would intensify it. A living atmosphere at 120 light-years would make the neighbourhood feel crowded, because 120 light-years is close enough to feel almost reachable in imagination. Yet our telescopes would still see no cities, no beacons, no obvious artifacts, only natural spectra and quiet stars. The contrast would sharpen, biology nearby, technology absent. We would be forced to separate life from company and realise they are not the same statistic. Time becomes part of the tension, because 120 light-years is nearby on galactic scales. Light from that system left when Earth was beginning to industrialise, when radio was a new phenomenon and cities were still dim at night. If life is there now, it could be elsewhere now, and we might still miss it because our searches are shallow. If life is rare, we might be seeing a statistical fluke close to home, a lucky draw from a sparse distribution. Either way, the distance turns the planet into a time capsule. The galaxy is old enough for many experiments, but not all experiments overlap in time. Civilizations could rise and fall in windows shorter than cosmic travel times, leaving no persistent beacon. A silent sky could be a timing problem, not an occupancy problem, because signals can be brief while stars endure. The Milky Way might be full of ruins and seedlings, separated by eras rather than by space. If so, we are listening to a choir that never sings in unison. There is also the possibility that biology is common, but detectable biospheres are not. A planet can host life that barely alters the atmosphere, especially if biology is confined to oceans or subsurface environments. A world can be alive and spectrally quiet, especially under thick clouds, low productivity, or rapid chemical recycling. Even on Earth, atmospheric signatures have changed dramatically over geological time, and for long periods oxygen was scarce. If an alien astronomer had looked at early Earth, would they have recognized it as alive? Oxygen, for example, is not a universal biosignature, it is a contingent one. It requires photosynthesis and a planet where oxygen can accumulate rather than being consumed by rocks, volcanic gases, and reduced minerals. Methane can be biological, but it can also be geological, and it can be destroyed quickly by ultraviolet light unless it is replenished. So the atmosphere becomes a riddle, a balance sheet of sources and sinks that can mimic life or hide it. The most convincing signature may be disequilibrium, but disequilibrium has multiple causes. K2-18b matters because it is detectable at all, and detectability is a filter we impose. We can only study transiting planets around small stars with favourable geometry, and we can only measure atmospheres that are not completely masked by clouds. Our sample is not the galaxy, it is the subset that casts shadows and yields readable spectra. The shadows are precious, but they are not representative by default. If we forget that, we risk mistaking convenience for truth. That selection effect can create illusions of frequency, and it can also hide real patterns. If we confirm life on an easy-to-observe world, we may overestimate how common it is elsewhere, because we found it where it was easiest to find. If we fail to confirm life on hard-to-observe worlds, we may underestimate because difficulty masquerades as absence. The absence of evidence is shaped by the difficulty of the measurement, and the difficulty is shaped by physics, not by biology. The universe may be full of life that sits below our current thresholds. so the discovery would reshape expectations, but it would not end debate. It would turn speculation into constrained inference, which is a different kind of mystery because the unknown becomes sharper. The universe would feel more alive and more evasive because it would offer a hint without a full explanation. We would have an answer, and then a sharper set of questions, and we would have to decide which questions deserve the next decade of observation. We can also place K2-18b on the timeline of galactic habitability, where chemistry and catastrophe compete. Metallicity rises over time, enabling more rocky planets and richer chemistry, and that trend is written into stellar populations. Yet high metallicity regions can also have more supernovae, more radiation, and more dynamical disruption, because star formation is more intense. The same spiral arms that host star formation can also host hazards, and the hazards do not ask whether a planet is ready. A habitable world must survive its neighbourhood as well as its own climate. The Milky Way may have a shifting habitable zone in space and time. Inner regions have more metals but more hazards, including denser stellar environments and stronger radiation fields. Outer regions are calmer, but may form fewer rocky planets early, delaying the onset of complex chemistry. Over billions of years, stars migrate through the disk, and their planets carry their histories with them, crossing environments like travellers. The galaxy is not a set of fixed addresses, it is a moving circulation. K2-18b's location is local, but its implication is global. If a nearby M-dwarf planet is alive, then long-lived stars could host biospheres for trillions of years, far longer than the Sun can. That would make the future galaxy more habitable than the past, simply because time is an ingredient. The dominant stellar population would become a vast reservoir of opportunity, where evolution can run long experiments. The universe would not be running out of chances, it would be just getting started. Yet M-dwarfs also challenge early survival, and the challenge is not subtle. Their long-active phases can strip atmospheres and drive harsh photochemistry, and their close-in habitable zones expose planets to that violence. A living K2-18b would imply either resilience, protection, or a late start after activity calmed. It would hint at magnetic shielding, atmospheric replenishment by volcanism, or deep ocean refuges that can wait out the storm. It might also hint that our assumptions about sterilization are too pessimistic. That possibility reframes the role of time again, and it changes what early means. Life might not need to appear early. It might appear when conditions stabilize and the atmosphere becomes less fragile. A planet could spend 1 billion years hostile, then become habitable for the next 100 billion, and the long calm could outweigh the early chaos. The window for biology could be delayed and still be enormous, especially around stars that barely age. If so, the galaxy's most common stars could be its most patient cradles. Now we return to the Drake factors we cannot yet measure, because this is where the statistics become existential. How long do biospheres persist once they start? And how often do they survive climate swings and impacts? How often do they produce oxygen, methane, or other strong atmospheric signatures that can be seen across light years? How stable are those signatures against stellar variability, ocean chemistry, and geological recycling? These are not abstract questions because they determine whether life is common yet invisible. A confirmed K2-18b biosphere would anchor those questions in reality. It would tell us that at least one non-Earth world maintains atmospheric disequilibrium at detectable levels, rather than keeping life hidden in the ocean. It would justify deeper surveys aimed at similar stars and similar planet sizes, because the class would look promising. It would also motivate better models of photochemistry, clouds, and ocean atmosphere exchange, because interpretation would become urgent. Once life is on the table, every molecule becomes more consequential, but it would also raise the standard for interpretation, because success changes the burden of proof. If one biosphere is confirmed, every ambiguous spectrum becomes a battlefield of priors, and the community's caution will be tested. Some teams will see life everywhere, and others will demand impossibly strict proof, because false positives would be humiliating. The community would have to negotiate what counts as confirmed in a universe that rarely offers certainty. In practice, confirmation may mean converging lines of evidence, not a single decisive signature. The documentary's tone stays mysterious because the data point clarifies and deepens the puzzle at once. Confirmation would reduce one uncertainty, but it would expose larger ones about frequency, diversity, and evolutionary trajectories. We would know life exists elsewhere, yet we would not know how it scales across star types and planet classes. We would have a second example and still not have a distribution, only a hint of one. The universe would feel less empty but more complex. We would also confront a philosophical shift that is easy to underestimate. The question would move from whether life exists to what life tends to become, given time and energy and chemistry. Does it remain microbial, hidden under clouds and oceans, content with chemistry and slow cycles, or does it repeatedly climb toward complexity, cognition and technology, leaving detectable scars on its planet? A living K2-18b would not answer that, but it would make the question unavoidable. The silence would feel less like emptiness and more like a missing chapter. If biology is common, then the gap is not in the first spark, but in what follows, and that is a different kind of loneliness. That gap could be environmental, evolutionary or sociological, and we would not yet know which. We would only know that the universe can start the story, and that starting is not the rarest act. The rest of the plot would remain hidden behind distance and time. At this stage, the responsible move is to set up the next tests, because implication is not confirmation. To move from implication to confirmation, we need evidence that breaks degeneracies. We need constraints on mass, pressure, clouds, and stellar contamination, and we need them with enough precision to rule out convenient alternatives. We need to know whether the spectrum is planetary or partly an artifact of the star. In other words, we need to turn a suggestive pattern into a robust physical model. We need repeated transits across instruments to test stability and rule out systematics, because a real atmosphere should behave consistently. We need broader wavelength coverage to separate molecules from aerosols, since hazes can mimic absorption by flattening the spectrum. We need emission and phase measurements to sample more than the Terminator, because the day side and night side can reveal temperature structure and circulation. Each method adds a new angle, and the angles together can triangulate the truth. The goal is not just detection, but diagnosis. Mass matters because it sets gravity, and gravity shapes the scale height of the atmosphere, controlling how strongly features appear in transmission. Pressure matters because it controls chemistry and line shapes, and it determines whether a surface could exist at all beneath the gas. Clouds matter because they can flatten spectra and hide deeper layers, turning rich atmospheres into featureless silhouettes. Stellar contamination matters because spots and faculae can masquerade as molecular absorption, especially for active M-dwarfs. If we misread the star, we misread the planet. We also need comparative planetology, not a single celebrity world. A pattern across multiple candidates would let us estimate fell with less bias, because a population is harder to overinterpret than a single case. A null result across many similar worlds would also be informative, because it would constrain how special K2-18b really is. Either way, the statistics would become less fragile, less hostage to one spectrum. The census would begin to look like a census, not a rumour. So the chapter ends with a pivot from cosmic statistics back to experimental design. If K2-18b is the first whisper, we must learn how to tell whispers from echoes, and how to tell echoes from our own instruments. The next chapter follows the concrete path from headline probability to hard confirmation, one test at a time. And behind every test is the same quiet question. What does one living world do to the meaning of all the others? The headline says 99.7%, but the lab hears a conditional probability, confidence inside a model, not certainty about life itself. In the press release, it reads like a verdict, crisp and final, as if nature has already signed the paperwork. In a seminar room, it reads like a sentence with hidden clauses, footnotes, and an asterisk that points to assumptions. A detection significance is a statement about how unlikely the data are under one null hypothesis, usually a carefully simplified one. It is not a universal measure of truth, and it is never a substitute for mechanism, causality, or physical plausibility. When the claim is life, the mechanism is the entire story, because biology is not a label, it is a process. This chapter is the pivot from suggestion to proof, where every shortcut becomes dangerous and every assumption becomes a target. If K2-18b is alive, the evidence must survive hostile scrutiny from people who want it to fail and who are trained to find cracks. That hostility is not cynicism, it is quality control, because nature does not grade on a curve. Replication is the first gate, because one transit can flatten noise, bias, and a star that happened to be quiet that day. Webb must watch multiple transits, spaced across the star's activity cycles and separated by months of stellar mood and rotation. A single light curve is a snapshot, like one frame of a film. A sequence is a test of persistence, and persistence is what turns an anomaly into a phenomenon. In transit spectroscopy, the signal is a small difference between two large numbers, which is why it is so easy to fool yourself. We measure starlight when the planet is not in front of the star, then we measure it again when the planet blocks a thin slice. The atmosphere's imprint is the tiny residual, sometimes tens of parts per million, left after subtraction, and that residual must be stable. Visually, it is almost cruel in its simplicity. A bright spectrum, then a nearly identical spectrum, then a subtraction that leaves a faint ripple. Those ripples are where molecules hide as slight changes in depth at specific wavelengths. The challenge is that the same ripple can be carved by the planet, the star, or the instrument. M-dwarfs change their faces with rotation, spots, faculae, and flares, and those surface features are not evenly distributed. Dark spots dim the star and deepen transits in a way that can look like absorption, especially when the spot coverage is wavelength dependent. Bright faculae do the opposite, and both effects vary with wavelength, mimicking the colour signature of an atmosphere. A real planetary signal should persist as the stellar surface pattern evolves, even as the star's patchwork rotates in and out of view. That is why teams want transits spread across different rotation phases, not clustered in one convenient week. If the feature tracks the star's rotation instead of the planet's orbit, the case weakens, because the planet cannot inherit the star's calendar. There's also the problem of unocculted spots, which the planet never crosses but which still alter the star's spectrum. They change the baseline against which the transit depth is measured, shifting the apparent radius as a function of wavelength. In practice, the planet can inherit a false colour from a star with a mottled photosphere, as if the atmosphere were painted on by starlight. Teams repeat the observations in different instrument modes, because systematics are mode-specific and detectors have personalities. Webb's near-infrared instruments can read out in different patterns, with different dispersers and different subarrays that trade field of view for stability. A molecule that vanishes with a different setup is a warning, not a mystery, because physics should not depend on readout geometry. Independent reductions are not politeness, they are a stress test. Two pipelines must converge on the same features from the same raw photons. One group may choose a different background model, or a different approach to correcting pointing jitter and spectral drift. Another may handle cosmic rays or bad pixels more aggressively, and those choices can sculpt faint features. If the result depends on a particular choice, then the choice is part of the signal, whether anyone likes it or not. That is an uncomfortable sentence, but it is often the honest one, and honesty is what keeps the field from drifting. The goal is not to win an argument, it is to find out which parts of the spectrum are truly anchored in the data. The community also demands pre-registered checks, because hindsight can manufacture confidence, and selection can masquerade as rigor. When you know where a feature should be, you can tune your extraction until it appears, especially when the noise is structured. Pre-registration forces you to declare your test before you see the answer, so the analysis cannot quietly chase the desired outcome. Every choice in extraction and detrending must be auditable, from the spectral trace position to the polynomial used for baseline drift. That audit trail is not bureaucracy, and it is not a performance for reviewers. It is how you make a claim portable, so another team can reproduce it without reading your mind. So we need to separate what the data detects from what the story claims it means. That separation begins with repeatability, then widens into new geometries and new kinds of light, each with different vulnerabilities. A spectrum can be real and still be misread, because interpretation is where the traps multiply. Transmission spectroscopy only samples the terminator, a thin ring where day meets night, and where chemistry can be strange. Winds can mix gases along that ring, and clouds can pile up at the boundary between hot and cold, changing the apparent altitude of absorption. The terminator is not the whole planet, and it is not even a typical place. It is a particular slice, observed through a particular lens. Confirmation requires leaving the limb and testing the whole planet, because a global atmosphere must make global sense. If the terminator suggests one composition but the dayside suggests another, the retrieval is incomplete, or the atmosphere is more layered than assumed. Nature can be complex, but it must still be consistent, because energy, chemistry, and circulation have to balance. The next step is emission spectroscopy during secondary eclipse, when the planet slips behind the star and the combined light briefly loses the planet's contribution. The difference isolates dayside thermal emission and composition, like turning off a faint lamp and measuring the change in a bright room. It is a subtle measurement, but it asks a different question, and a different question can break a stalemate. Emission constrains temperature structure, which controls line strengths and retrieval degeneracies, and it does so more directly than transmission. A molecular band can deepen because the molecule is abundant, which is the tempting interpretation. It can also deepen because the temperature gradient makes the band more contrasty, which is a purely physical effect that can impersonate chemistry. It also tests whether the 120-degree force narrative matches any emitting layer, or whether it is a simplification that collapses a vertical atmosphere into one number. Planets do not have a single temperature, even when headlines insist they do. They have profiles, and those profiles decide what photons escape, from which altitudes, and with what spectral fingerprints. Brightness temperature is not surface temperature, and it can come from high altitudes where the air is thin and the view is clear. A warm brightness layer could sit above a cold boundary, like a thermal skin floating over deeper weather. It could also sit above a dense, crushing layer where no light escapes, hiding the interface that matters most for habitability. In the mid-infrared, the atmosphere can become opaque in different bands, and each band can probe a different altitude. That means one instrument can sample multiple layers without ever touching the surface, simply by changing wavelength. The spectrum becomes a vertical scan, translated into wavelength, and the planet's structure is encoded in where the light originates. If emission shows an inversion or unexpected gradients, transmission fits must be revisited, because the assumed profile is a hidden prior. A wrong temperature profile can invent molecules to rescue a fit, and the math will do it obediently. It is not fraud, it is mathematics doing what you asked, and that is why cross-checks matter. Retrieval algorithms are powerful because they search vast parameter spaces, exploring combinations no human would try by hand. They're also dangerous because they will always find a best answer, even when the data are ambiguous and the model is misspecified. The only antidote is cross-checking with physics, and emission is one of those checks. Phase curves raise the stakes further, because they track light over the full orbit and turn a single spectrum into a movie. They map heat redistribution and hint at winds, clouds, and weather regimes, even when the planet is a point of light. The planet becomes a rotating object, not a static diagram, and rotation reveals dynamics. A tidally locked world should show a predictable day-night contrast if the air is thin, because heat cannot travel far before it radiates away. The dayside bakes under constant starlight, building a persistent thermal maximum. The night side radiates into space, and the temperature difference can be extreme, shaping chemistry and cloud formation. A thick atmosphere should smear heat and shift the hotspot downwind, because winds transport energy before it can radiate away. On hot Jupiters, we see that shift as an offset in the phase curve peak, a measurable delay in the brightest point. On smaller worlds, the same physics should apply, though the details change with gravity, composition, and rotation. Phase variations can also reveal patchy clouds that migrate, flattening features at some phases and sharpening them at others. That variability can mimic changing chemistry if geometry is ignored, because the visible hemisphere is changing with time. A cloud deck moving across the dayside can look like a gas disappearing, when it is really just being hidden. The goal is not a pretty curve, but a circulation constraint that retrievals must obey, even when the chemistry looks persuasive. Climate physics becomes a cross-examination of the chemistry claim, forcing the story to conserve energy and momentum. If the inferred winds are impossible, the inferred molecules are suspect, because they were asked to solve the wrong problem. There is also a deeper point hiding in the phase curve: energy balance. The planet absorbs starlight and must re-radiate it, and the timing of that re-radiation encodes atmospheric inertia and heat capacity. When the curve lags, the air is storing heat, like a thermal flywheel. When it snaps, the air is thin, and the surface or upper atmosphere responds quickly. Cloud and haze discrimination is the next hard wall, because aerosols counterfeit spectra with ruthless efficiency. A haze can mute molecular bands, tilt continua, and create slopes that resemble absorption, especially when the signal is already small. You can fit a haze with molecules, or fit molecules with haze, unless you broaden the view and force the models to commit. Multi-wavelength coverage from near IR to mid-IR breaks key degeneracies, because scattering and absorption behave differently across that span. In the near-infrared, many molecules overlap, and broad bands can blur into one another. In the mid-infrared, their vibrational bands can separate more cleanly, giving the spectrum more distinct landmarks. Small particles scatter strongly at shorter wavelengths, steepening the slope and making the planet look larger in the blue end of the infrared. Larger particles flatten the continuum and hide deeper bands, creating a grey veil that suppresses contrast. The particle size distribution becomes a silent parameter that can dominate the retrieval, even when no one mentions it in the headline. Near IR bands can suggest water or methane, yet hazes can blur the same regions by adding a grey opacity that washes out structure. A spectrum with softened features can be read as low abundance, which is a tempting conclusion. It can also be read as high clouds, which is a completely different atmosphere wearing the same mask. Mid-IR features can separate true molecular absorption from aerosol opacity, because many aerosols are less featureless there, and some cloud species become partially transparent. Some hazes have their own signatures, and some clouds reveal lattice vibrations that leave faint imprints. The mid-infrared is not a magic truth machine, but it changes the balance of evidence. MIRI coverage becomes decisive when broad features overlap in the near IR, and when the retrieval keeps trading one molecule for another. If the mid-IR does not cooperate, the life-leaning retrieval loses leverage, because it cannot generalize beyond one window. A claim that survives only in one window is a fragile claim, and fragility is what skeptics hunt. The team must also test multiple cloud parameterizations, not one convenient haze layer that behaves like a dial. Real atmospheres have vertical structure, microphysics, and patchiness, and those details matter for where light is blocked. A robust biosignature survives when cloud priors are widened, not tightened, and when the model is allowed to be inconvenient. This is where the 99.7% number becomes a trap, because it compresses uncertainty into one headline. The real question is which alternatives remain plausible, and how much fine-tuning each alternative requires to match the data. A good explanation is not just possible, it is stable, and stability is what you get when physics is doing the work. In practice, teams run retrievals with different priors, different opacity databases, and different assumptions about chemical equilibrium and vertical mixing. They compare Bayesian evidences, but they also look at residuals with human eyes, because humans still recognize patterns machines ignore. A model can win statistically while leaving structured leftovers that whisper systematic in the language of correlated noise. High-resolution spectroscopy is the conceptual gold standard, even if it is brutally hard for a small planet around a dim star. Resolving individual lines can identify molecules unambiguously and test isotopes, turning broad bumps into specific fingerprints. Instead of smooth hills, you see a forest of narrow features, each one tied to quantum transitions. At high resolution, Doppler shifts become a tool rather than a nuisance. The planet moves at tens of kilometers per second, and its lines slide back and forth across the stellar spectrum as it orbits. That motion can separate planet from star, even when the star dominates the light, because the planet's pattern is moving while the star's pattern is mostly fixed. Isotopic ratios can discriminate pathways, because biology and geology fractionate differently under different reaction networks and energy constraints. On Earth, life prefers lighter isotopes in many contexts, leaving measurable imprints in carbon, sulfur, and nitrogen reservoirs. Those imprints are not universal proof, but they are a powerful constraint, especially when multiple gases tell the same story. A consistent isotopic pattern across gases would tighten the causal story, because it is harder to fake multiple ratios at once. It is one thing to match an abundance within error bars, which models can often do. It is another to match the subtle bookkeeping of isotopes, where each pathway leaves a different mathematical signature. But high resolution demands photons, stability, and a bright enough star, and K218b is not an easy target. For K218b, it may require stacking many events and using the largest ground telescopes, where every transit becomes another brick. That means years, not weeks, and it means living with weather, scheduling, and the slow grind of accumulation. Ground-based ELTs can complement Webb by resolving line forests that Webb blends, especially in windows where Earth's atmosphere allows. Cross-correlation can pull faint molecular patterns out of noisy spectra, using a template as a matched filter that rewards consistent line spacing. It is a technique built for signals that hide in plain sight, and it turns motion into separation. The synergy is strategic, not redundant, because Webb provides stable broadband baselines and exquisite calibration over long continuous observations. ELTs provide sharp line identification and Doppler separation from the star, which is a different kind of leverage. Together they can test whether the same molecule appears in two fundamentally different measurement regimes, which is exactly what robustness looks like. Temporal biosignatures are the thriller element, because time can reveal an engine rather than a snapshot. If gases swing together in correlated ways, metabolism becomes harder to dismiss, because correlation implies coupling. A living system is not just chemistry, it is chemistry with feedback, sources and sinks locked in a dynamic tug-of-war. Seasonal cycles would be powerful, but they must be physically plausible for the orbit and the planet's rotation state, not merely suggestive. A tidally locked planet may show weather cycles, not Earth-like seasons, because its illumination pattern is fixed. Its seasons could be driven by stellar variability or atmospheric dynamics, and those drivers must be modelled, not assumed. The key is correlation and phase, not mere variability, because many non-living processes fluctuate on their own. Biology should couple sources and sinks in patterns that geology struggles to synchronize, especially when reaction lifetimes are short. The atmosphere becomes a ledger, and the question is who is doing the accounting? Rocks, sunlight, or something that eats and breathes? For example, methane rising with an oxidant proxy would be suspicious if lifetimes are short, because the gases should destroy each other quickly. The implied replenishment rate becomes a quantitative demand, not a poetic hint. You can ask, in numbers, how many molecules per second must be produced, and whether any known abiotic mechanism can pay that bill. Those numbers matter because they connect spectra to fluxes, and fluxes connect to plausible engines, which is where speculation meets constraints. A planet can hold a lot of gas, but it cannot produce it arbitrarily fast without leaving other signatures. If the required flux exceeds volcanic or hydrothermal budgets, the story tightens, and the remaining explanations become fewer. Yet volcanism can also pulse, and photochemistry can also oscillate under flare-driven UV, especially around active M dwarfs. Temporal claims must be matched against stellar monitoring and flare histories, including ultraviolet proxies and chromospheric activity. Otherwise, you could be watching the star's mood, not the planet's metabolism, and mistaking variability for vitality. Stellar contamination remains a constant adversary, because the star is part of the measurement and not a passive backlight. Spots and faculae change the apparent transit depth with wavelength, which can imprint false slopes and pseudobands. That produces features that can look planetary even when the planet is innocent. Out-of-transit spectra and long baseline photometry are required to model the stellar surface, including how its heterogeneity evolves over rotations and longer magnetic cycles. Without that context, retrievals can fit the star with fake molecules, because the math is eager to explain structure. The planet becomes a canvas for stellar freckles, and the interpretation becomes a portrait of the wrong object. There is also the subtlety of flare aftereffects, where ultraviolet bursts alter the star's chromosphere and change line cores and continuum levels. Even if the flare is not seen in the transit, its aftermath can persist, shifting the baseline for minutes or hours. A careful team watches the star before, during, and after, because timing is part of the evidence. The instrument itself must be interrogated, because drift can masquerade as a slope, and because detectors remember what they saw. Teams check detector ramps, pointing jitter, background subtraction, and wavelength calibration, and they do it with a suspicious eye. They look for correlations with spacecraft temperature and pointing, because hardware has rhythms that can mimic astrophysics. They inject synthetic signals into raw data to test recovery and bias, because a pipeline should be able to find what you hide in it. A pipeline that cannot recover known truths cannot be trusted with unknown ones, no matter how elegant the plots look. Injection tests turn faith into measurement, and they expose where the analysis is brittle. Sometimes the most revealing plot is not the spectrum but the residuals against time, where systematics leave their footprints. If the residuals show a repeating pattern, you suspect hidden structure that the model did not capture. If they show white noise, you breathe easier, though you still do not celebrate because white noise can be a temporary illusion. Contextual constraints decide whether the life hypothesis is even coherent, because chemistry depends on the kind of planet you are describing. mass must be measured to infer density, gravity, and likely composition, which in turn shapes scale height and observable features. Without mass, radius is a silhouette without weight, and a silhouette can mislead. Radial velocity can weigh the planet by the star's wobble, but M dwarfs are noisy in ways that imitate planets. Stellar activity can mimic RV signals and inflate false precision, especially when spots distort spectral lines. A rotating spotted star can create a fake periodicity that looks planetary, and the deception can be remarkably convincing. Teams use activity indicators, like H-alpha or calcium lines, to separate stellar jitter from orbital motion, and they compare signals across wavelengths. They also observe in the infrared, where spots have less contrast and the activity imprint can weaken. Even then, the line between signal and star is thin, and the uncertainty must be carried honestly. Transit timing variations can provide mass if other planets tug the orbit, and those tugs show up as early or late transits. TTVs are indirect, but they can break the mini-Neptune versus rocky ambiguity by revealing gravitational interactions. They also hint at the architecture of the system, which matters for formation history and volatile delivery. Density is the fork in the road for interpretation, because it decides whether the planet is puffy or compact. A low density implies a thick H2 envelope that weakens surface life claims and complicates chemistry, because hydrogen changes reaction pathways. Hydrogen changes everything, from scale height to photochemistry, and it can keep reduced gases around longer. A higher density supports a rocky or water-rich world with a more accessible interface, though accessible is still a hypothesis and not a guarantee. Even then, high-pressure ice could isolate the ocean from the crust, sealing off geochemical cycling. The ocean could exist and still be chemically cut off, which would change what life could do. Pressure constraints matter because chemistry depends on collisions and vertical mixing, and because many gases behave differently under different pressures. Line shapes and continuum levels can hint at pressure through broadening, where higher pressure smears line wings. But clouds can obscure those clues and flatten the spectrum, stealing the very diagnostics you want. If K2-18b is a mini-Neptune, the story shifts from surface biosphere to atmospheric chemistry, and the bar for life rises. A deep envelope hides the boundary conditions, including whether there is liquid water anywhere accessible to energy gradients. You cannot easily argue for oceans and rocks when you cannot see where the air ends, and when the interface may be unreachable. That does not make life impossible, but it changes the kind of life you are implying, and it changes the evidence you need. It also changes the false positives, because hydrogen-rich atmospheres can sustain reduced gases more easily under some UV regimes. What looks like a biosignature in one regime can be ordinary in another, and context decides which regime you're in. False positive kill tests are the discipline that keeps the thriller honest, and they are often less glamorous than the detection itself. Every biosignature candidate must be attacked with photochemical and geochemical modelling, using the best constraints available. The goal is not to defend the claim, but to try to break it, because a claim that cannot be broken is the one you keep. Models must use the star's measured UV spectrum, not a generic template, because UV controls radical production and chemical lifetimes. It also controls haze formation and oxygen false positives, which can rewrite an atmosphere without any biology. Around M dwarfs, the UV environment can be spiky and episodic, and that spikiness can dominate chemistry. Teams test whether methane and ammonia can persist abiotically under realistic UV mixing, including vertical transport that can replenish upper layers. If the models sustain them without life, the claim weakens sharply because uniqueness evaporates. If they destroy them quickly, the replenishment problem returns, and the implied source becomes the next target. They test whether water loss and hydrogen escape could leave misleading oxidants, especially if the planet once had more water than it does now. An oxygen-rich atmosphere can be a grave marker for oceans, not a celebration, depending on the history. The same gas can mean life or loss, and the difference is written in context and timescales. They test whether serpentinization and hydrothermal fluxes can meet the required budgets, because rock-water reactions can generate hydrogen and methane under the right conditions. If geology can pay the bill, biology loses its uniqueness, and the interpretation must become more cautious. The question becomes one of rates and persistence, not mere possibility. They test whether episodic volcanism can reproduce both abundance and variability, because outgassing can be bursty and uneven, A single eruption can dominate a few transits and fake a long-term pattern, especially with sparse sampling. In sparse data, a short event can masquerade as a climate, and the only cure is more time. They also test whether aerosols created by photochemistry could mimic the same spectral features attributed to gases, because haze chemistry can be a master of disguise. A haze can be a product of methane chemistry, and it can also hide methane's bands, creating a self-masking system. The atmosphere can both reveal and conceal its own ingredients, depending on particle formation and transport. So the question becomes a structured elimination problem, not a single dramatic detection. Each surviving alternative narrows the space where life can hide, and it also narrows the space where mistakes can hide. The process is slow, but it is the only process that earns belief, because belief is what remains after the easy explanations are gone. Institutional reality shapes the pace, because telescope time is scarce, and reputations are fragile, and both are rationed. Competing teams will race to confirm, refute, or reinterpret, often using the same public data with different methods. That competition can be tense, but it is also productive, because disagreement forces clarity. Peer review becomes a second instrument, designed to find weak links in the inference chain and to demand missing tests. Reviewers will ask for raw data access, robustness checks, and open code, and they will ask for alternative models to be tried. They will ask why one baseline was chosen instead of another, and whether the choice was justified before the result was known. Skepticism is not hostility, it is the field's immune system, and it has a long memory. Extraordinary claims are treated as likely wrong until they become hard to kill, which is why the burden is asymmetric. That standard is not cruelty, it is how science avoids being fooled by its own hopes, especially when the prize is existential. The human side of certainty is where the risk peaks, because a single number like 99.7 becomes a headline, then a promise, then a trap. The public hears almost certain, which sounds like a finish line. Scientists hear under assumptions, which sounds like a beginning, and between those meanings, misunderstandings thrive. Scientists must communicate what the number actually means, including priors and model dependence, without drowning people in jargon. They must separate detection significance from biological attribution, even when the audience wants one word. A spectrum can be statistically strong and biologically ambiguous, and that ambiguity is not a failure, it is the honest state of the evidence. Ethics matter because public trust is a finite resource, and it is easier to spend than to earn back. Overclaims can poison future discoveries, even when later evidence is real, because the audience learns to brace for disappointment. A disappointed audience becomes a suspicious audience, and suspicion makes careful science harder to hear. The community remembers past overreach, from canals on Mars to vegetation analogies in ambiguous spectra, and those stories still shape caution today. The lesson is that interpretation must lag behind measurement, not outrun it, even when the narrative is irresistible. In astronomy, the distance between signal and story can be light years wide, and it is crossed one test at a time. If the life hypothesis collapses, it will likely collapse on one of three fronts, and each front has its own signature. The signal fails replication, the star explains it, or the planet is a mini Neptune with an envelope that rewrites the chemistry. None of those outcomes are trivial, because each teaches a different lesson about how we should measure and infer. If it survives, it will do so by converging lines of evidence that agree across methods and across teams, even when they disagree about everything else. Transmission, emission, phase curves, and context will tell one consistent story, with no hidden contradictions. The same molecules will appear where physics says they should, and they will persist when the analysis choices change. At that point, the claim shifts from intriguing to unavoidable, even if it remains incomplete and even if the word life stays carefully qualified. We would not know the organism, and we would not know the ecology, and we would not know the history. But we would know the planet is chemically active in a way that demands explanation, and that demand would not go away. Future missions extend the interrogation rather than ending it, because confirmation is rarely a finish line. New space observatories can add broader mid-IR coverage and higher stability over longer baselines, which is what slow signals require. They can watch longer, and they can watch quieter, and they can catch the planet in different stellar states. Direct imaging concepts remain distant for K2-18b, but they shape the long game and the way engineers think about contrast and starlight suppression. One day, separating planet light from starlight could test surfaces and clouds directly, turning inference into something closer to seeing. That is the dream behind today's careful spectroscopy, and it is why the field invests in patience. For now, Webb remains the anchor, and everything else is leverage: ground telescopes, modelling, stellar monitoring, and the discipline of repetition. The roadmap is patience, redundancy, and a willingness to be disappointed by the truth, because truth does not care what we want. In science, disappointment is often the price of accuracy, and accuracy is what lasts. We step back from the lab and the telescope because the climax is not a single plot twist or a single plot point on a graph. It is the moment we decide what counts as knowing and what level of uncertainty we can live with. It is the moment we admit how hard it is to be sure, even when the data are beautiful. If the evidence holds, K218b becomes more than a spectrum and a shadow, more than a transit depth and a retrieval plot. It becomes a second origin story and a new baseline for cosmic loneliness, because it would imply that life is not unique to one world. It would suggest that biology is not a miracle, but a tendency, emerging when conditions allow and chemistry has time. If the evidence fails, the failure still teaches us how planets counterfeit life, and it teaches us where our methods are brittle. The universe would be telling us that chemistry can wear convincing masks, and that our instruments can be seduced by them. That lesson would make the next claim harder but also cleaner, because we would know what to fear. Either way, the mystery deepens, because our methods become part of the story, and our caution becomes part of the discovery. The closer we get to proving life, the more rigour we must bring. More replication, more cross-checks, more humility, and more time. The drama is not in the announcement, and it is not in the number. The drama is in the discipline. The final chapter asks what we do with that rigour and that possibility, once the data stop being just data. A single world can redraw the map, but only if we earn the right to believe it, and that right is earned through tests that could have failed. Until then, the number stays conditional, and the question stays alive. The central question stays open, because Webb measures light and we infer life. Webb does not sample oceans or soils, it collects photons that have crossed space for decades. What Webb can claim now is narrow and powerful, and that restraint is part of the method. A real transit exists, meaning the planet's silhouette repeatedly trims the star's brightness by a measurable amount. During that transit, a spectrum shows small, wavelength-dependent features consistent with certain molecules. Visually, it is almost underwhelming at first. A smooth light curve with a shallow dip, then a forest of points with error bars. Yet inside that thin ring of starlight, the atmosphere leaves fingerprints, because gases absorb infrared light at specific energies. The planet's limb becomes a laboratory, where temperature, pressure, and composition shape the depth of each spectral ripple. The signal is tiny, often tens of parts per million, and that scale explains the caution. The interpretation is the fragile step because retrievals depend on priors, clouds, and stellar contamination. A retrieval is not a direct reading of air. It is an inversion where many atmospheres can mimic one curve. Priors quietly matter because they encode what we think is plausible before the data speak. Clouds and hazes matter even more because they can flatten features and hide deeper layers from view. Stellar contamination matters because the star is not a perfect lamp, and spots and faculae imprint their own spectral texture. The headline 99.7% is not a life probability, and it is rarely a universal truth. It usually means a feature is unlikely under a chosen null within a chosen model family. Change the null, change the family, or change the treatment of correlated noise, and the number can shift. In scientific language, it is confidence in a signal pattern, not confirmation of a biological cause. It is closer to saying, this wiggle is probably real, than saying, this world is alive. Alternative hypotheses remain on the table, including photochemistry under M-dwarf UV, episodic outgassing, and haze physics. Around M-dwarfs, ultraviolet bursts can drive chemistry far from equilibrium, building molecules that look suggestive in isolation. Volcanism can also be intermittent, and a temporary plume can bias a snapshot spectrum. Haze microphysics can generate broad absorption that masquerades as specific gases, especially when the data are sparse. Instrument systematics and pipeline choices can also sculpt weak features into persuasive stories, because calibration is itself a model. So we separate detection, interpretation, and confirmation, and we keep them separated on purpose. Detection says the shadow and the spectral ripple are repeatable across visits and across detectors. Interpretation says those ripples belong to specific gases at specific abundances in a physically consistent atmosphere. Confirmation says biology is the best remaining engine after realistic abiotic models fail. That last step is slow by design, because extraordinary claims can hide inside ordinary uncertainties. What would constitute confirmation is not one molecule and not one sigma threshold. It is converging evidence across methods, epochs, and teams, with a coherent physical planet underneath. We would want the same story to survive different retrieval codes, different assumptions, and independent reductions. We would want multiple instruments to agree because each has different systematics and different spectral leverage. The goal is not drama, it is durability. Mass and density must narrow the planet class because chemistry means different things in different envelopes. A low-density mini-Neptune can host a deep hydrogen atmosphere where many molecules are diluted and misleading. A denser world can support a thinner envelope where surface, atmosphere exchange becomes plausible. Pressure and clouds must be constrained because they set the altitude we are actually sampling. If a high cloud deck blocks the lower atmosphere, then we are reading only a cold, thin layer, not the planet's full chemical engine. Stellar monitoring must show the features do not track spot cycles or flare aftermath. That means watching the star outside transits, mapping its variability, and checking whether the spectrum changes with time. Emission and phase data must agree with transmission, so the atmosphere conserves energy and makes global sense. If the day side glows at one temperature while the limb implies another, the model must reconcile them or be rejected. Even the planet's circulation matters, because winds redistribute heat and reshape chemistry on a rotating world. If life is confirmed, biology changes first, because Earth stops being the only example. The history of science is full of single-sample illusions, and astrobiology has lived with one data point for centuries. We would test convergent evolution, asking whether chemistry repeatedly finds similar solutions under similar constraints. Would life favour familiar building blocks because they are optimal, or simply because Earth got there first? We would also take alternative metabolisms seriously, including sulfur, hydrogen, or photochemical pathways unlike our own. The question becomes less, is it like us? And more, what does selection do with the materials available? A confirmed biosphere on a likely ocean world would expand the definition of habitability beyond continents and shallow seas. It would force us to model ecosystems that live under clouds, under ice, or in atmospheric layers. It would also sharpen the question of detectability, because life may be common yet spectrally quiet. On Earth, biology can be loud in oxygen and methane, but it can also be subtle, localized, and seasonally hidden. We would ask which biospheres announce themselves and which ones whisper. Planetary science would shift towards stability, because life needs time more than perfection. We would ask how climates persist around variable M dwarfs and what protects atmospheres from early erosion. Young red dwarfs can be violent, and their long active phases can strip volatiles unless a planet has shielding or replenishment. We would treat circulation, haze microphysics, and volatile cycling as biosignature context, not background detail. The climate system becomes part of the evidence because chemistry is never isolated from physics. Cosmology would absorb the shock more slowly, but the implications would be permanent. One confirmed living world nearby would raise the prior that life emerges when conditions allow. It would not solve the origin of life, but it would constrain it, because rarity would no longer be an assumption. The night sky would stop being mostly emptiness and start looking like a sparse ecology. Even our metaphors would change, because worlds would mean more than rocks under starlight. Yet the quiet revolution also includes the possibility that life is not confirmed. If K28b becomes a false positive, the search still advances because failure teaches the universe's disguises. Each mistaken biosignature improves photochemical models, cloud parameterizations, and stellar contamination corrections. It teaches us which combinations of temperature, UV, and mixing produce deceptive spectra. It also teaches humility, which is not a mood, but a tool. False positives also harden our standards, so the next claim is cleaner and harder to kill. They guide instrument design because they reveal which wavelengths and resolutions break degeneracies. A broader bandpass can separate overlapping absorption features, while higher resolution can isolate narrow lines from smooth haze. They also guide target selection because they show which stars and planet classes are interpretable. Some systems are simply too noisy, and some atmospheres are too opaque to answer the life question cleanly. This is the philosophical shift that survives either outcome. Earth becomes one example rather than the template, and our categories become provisional. The universe becomes a generator of niches, where habitability is a spectrum and life is a possible phase. For centuries we argued from absence because we had no other air to read. Now we are learning to argue from spectra, and spectra demand discipline. Practically, K218b becomes a signpost for the next generation of telescopes. It tells us where to spend time, which atmospheres are legible, and which confounders dominate. It pushes us toward comparative planetology, because populations reduce the tyranny of one spectrum. A single world can mislead, but 100 worlds reveal patterns, and patterns are where science becomes confident. We return to the journey that began as a faint dip in starlight in Leo. That dip became geometry, then a spectrum, then a chemical narrative written in infrared. In the mind's eye, the constellation is still, but the data are alive, lines rising and falling as if the planet is breathing. Now it becomes a discipline, where wonder is permitted but proof is earned. In the end, Webb is still staring into Leo, listening to alien air through a thin ring of light. Whether that air is alive or only looks alive, we have learned to read the universe differently. The faint dip is no longer a curiosity, and it is no longer just a planet count. It is the beginning of a new era of exploration, where the smallest shadows can carry the largest meanings. We began with a tiny repeatable dip in starlight from Leo, a shadow that turned into mathematics, then into a world. From that light curve, James Webb moved to something far more delicate, a transmission spectrum where tens of parts per million decide what the air might be. Along the way, we learned why every step is conditional. Stellar spots can paint false colours, clouds can erase fingerprints, and retrievals can mistake a plausible story for a unique one. We also learned that the headline numbers hide their fine print, because 99.7% usually measures the strength of a feature against a chosen null, not the probability of life itself. A 3 sigma bump can be real and still be misidentified, or correctly identified and still be abiotic or vanish when the next dataset changes the noise model. That is why the atmosphere's barcode must be interrogated across instruments, across epochs, and across independent pipelines, until the signal survives adversarial tests rather than friendly ones. K216b's supposed warmth taught us another humility, because about 120 degrees can mean equilibrium bookkeeping, an emitting layer in infrared, or a modelled surface that may not exist. Around an M dwarf, where UV bursts and long-term activity sculpt chemistry, habitability is not a thermostat reading, but a dynamic negotiation among radiation, circulation, and shielding hazes. And beneath the spectrum sits the planet's unresolved identity, because mass, density, and pressure decide whether we are seeing a rocky world, a water world capped by high-pressure ice, or a mini Neptune whose deep surface is forever hidden. When the conversation turns to life, the standard shifts again, from could it to what else could. And that is where disequilibrium becomes both tempting and treacherous. A chemical pairing that should not coexist can be a living metabolism, yet it can also be geology, photochemistry, escape, or a star's restless face leaking into the measurement. Even the rumoured pulsing, or variability, if it holds up, must be asked to obey physics first, because biology is not the only engine that can make an atmosphere change. So the path forward is not one heroic observation, but convergence, a slow tightening of possibilities until the remaining explanation is no longer merely exciting but unavoidable. Repeat transits must agree across NIRIS, NUSPEC, and MIRI. Stellar monitoring must map spots and flares in real time, and injection tests must prove that pipelines cannot manufacture the very molecules they seek. Emission spectra and phase curves must anchor temperature profiles and circulation, while RVs or TTVs pin down mass and density, turning maybe ocean and maybe hydrogen envelope into measurable fates. And if K218b ever crosses the line into confirmation, it will not only answer a question about one world, it will rewrite our priors about many worlds. One biosphere, even found through selection effects and biased targets, would still transform the census problem, because it would prove that life can arise and persist under conditions unlike Earth's. Yet if the signal collapses, into contamination, non-replication, or a mini-Neptune context, the lesson remains profound, because the universe would have forced us to build a sharper definition of evidence. In that sense, the documentary's quiet revolution is not a promise that Webb has found life, but a map of how knowledge is earned at interstellar distance. Detection is repeatability, interpretation is physical consistency, and confirmation is what remains when the best abiotic models have been given every chance to win. The closer we get to a living world, the more the universe demands patience, and the more we must treat wonder as a hypothesis that has to survive the cold light of replication. So did James Webb truly detect a living world on K2-18b, or a cruel cosmic mirage shaped by noise, clouds, and assumptions? For now, the honest answer is that Webb detected a compelling atmospheric signal, and the 99.7% is not life's probability, but a challenge, an invitation to prove or to falsify with harder data. K2-18b is still only a shadow and a spectrum, yet it has already redrawn the map of what we dare to consider possible. If life is there, it will be confirmed not by a headline, but by a chorus of independent tests, because in the universe, the most extraordinary truths arrive the same way starlight does, patiently, one photon at a time. Stay curious but demand rigor. Follow the next observing campaigns and the open debates, and let the evidence, not the excitement, tell us what is alive.